welcome. So it's a pleasure for me to introduce Patrick Popescu-Pampu from University of Lille in France. His lectures are about combinatories of plane curve singularities. So there are two sessions, if I well understand. As Ignacio explained, that I have to say you that this is a lecture of so it's not only a talk, so it's two sessions. So please ask questions, stop speaker, any comment. So I'm sure that Patrick is happy if people stop in and ask questions and details. So thank you, Patrick. It's your time.
Thank you very much. Thank you very much for having invited me here. It's a great honor to open this conference with the first part of this mini course, in a nutshell, mini course, Combinatorics of Plane Curve Singularities. So it's a great opportunity to say that I was always very happy in Spain with Spanish mathematicians, and I think this is a good image of the atmosphere I always felt in this country, in particular due to Alejandro and Enrique. So happy birthdays, Alejandro and Enrique, and best wishes for great new creative years. Dichosos los ojos que les ven. So I also have to thank my collaborators, because this mini course is based on 10 years work, which led to several papers, and also to the opening chapter in a series of books which I think now are the reference books for the geometry and topology of singularities. The first chapter is called exactly like this mini course, the Combinatorics of Plane Curve Singularities, but it has a subtitle, How Newton Polygons Blossom into Lotuses. And we dedicated it to Bernard Tessier, who was our PhD advisor, and who made us feel that first, in order to get new intuitions about any phenomenon about singularities, we should look at plane curve singularities. So that's why we love them, and we tried to make a text which helps people to touch them concretely. So in fact, you have to know that philosophically my talk today is aimed to drawing. So I think it's most useful if you try after the talk, you can ask me questions, to really do the drawings which I will show. So first, what means plane curve singularity in this talk? Well, it's a germ of reduced plane curve over any algebraically closed field of characteristic 0, but at some moment we will have to specialize to the complex numbers, namely when we will want to think about the topological type of the plane curve singularity, meaning a link in the three-dimensional sphere, a construction which is possible only when the field is that of the complex numbers. The last line is written in fanciful post-Grothendieck terms, but mainly we won't think in this way. We will think very concretely about the internal structure of singularity. So usually the combinatorial type, and I emphasize combinatorial type, it is what we call usually topological type when we think over the complex numbers. But we say combinatorial type precisely because over an algebraically closed field of characteristic 0, an arbitrary one, we cannot make the same topological construction. So the combinatorial type is analyzed mainly using either Newton-Puiseux series, sequences of point blowing ups which lead to the minimal embedded resolution, or in the topological way through a link in S3. And the three tools allow to construct trees. The first one, using Newton-Puiseux series, Puo and Blue introduced a tree in 1977. Then Eggers, at the beginning of the 80s, introduced another kind of tree which is related to the Puo-Blue tree. I will explain at some moment how. And Wall, Terry Wall, refined, in fact, the Eggers construction. He modified it a little, and I will explain why Wall's modification is important. Then, sequences of point blow-ups led to what we believe is the first tree associated to singularities, which was introduced during the First World War by Federico Enriquez, and you find it in his famous treatise with Kisidi about algebraic curves. And also leads to something else, which is a dual graph of the final embedded resolution. So sequences of point blow-ups lead to two kinds of trees. And finally, links in the three-dimensional sphere led through work of Ziebenmann and of Eisenbahn and Neumann in the 80s to so-called splice diagrams. And the aim of this mini course is to explain how the notion of lattice allows to unify those various viewpoints. So the main object which I want to present you is that of lattice, and the lattice is like this. So for the moment I don't say anything about it, so just please look at it and try to analyze how it is built. Are there any questions for the moment? No? So let's continue. I will first recall what it means to get an embedded resolution of a plane curve singularity. I simply write z of f of xy as the zero locus of f of xy, and as I told you, this means the germ of the curve defined by the equation f equals to 0. So, how to get an embedded resolution? You see, from time to time, I will show you a page with a question and an answer. And sometimes there will be pages with two questions and two answers. And systematically, the questions will be in black, and the answers will be in blue. And the answer will be very short, and then I will develop it. So, in some sense, I will blow up the short answer to make its internal structure visible. So, how to get an embedded resolution? Well, in an iterative process by blowing up points. And once one learns first this, in general one learns it on the cusp. So the cusp, the easiest way to make this singularity appear is through the equation y2 equals to x cubed. So here you see zero loci of y2 minus x cubed, represented schematically here. And algebraically speaking, to blow up the origin of the plane of xy means to make two changes of variables. Either x is u1, u2, and y is u2, or symmetrically x is v1 and y is v1, v2. This means that one replaces the plane C2 by a new surface which can be obtained by gluing two affine planes, one of the coordinates v1, u2, and one with the coordinates v1, v2. And concretely, one makes these changes of variables here. One factors by the highest grade monomial which divides both terms, and one gets a new curve, which is called the strict transform of the initial curve. And in this example, the new curve, in fact, passes through the origin of only one of the two charts. And it's the only one which I drew here. It is the chart of the coordinates v1 and v2. And the first equation is replaced by the equation v2 squared minus v1. So here we see that we got a smooth curve, which means that abstractly our singularity is resolved. But this smooth curve is in fact tangent to the exceptional divisor, which is the preimage of the origin. By the way, you see that there is here a rule for colors. If I blow up a point, I color it, and the exceptional divisor, which appears in this way, has the same color. So here, the strict transform is not transversal to the exceptional divisor. That's why one blows up again this point, represented in blue now. Like this, one creates a new curve, E1, and when one computes the new strict transform, one gets now again a smooth curve, which is transversal to it. It is transversal to both components of the exceptional divisor, here the blue and the red one, but their union is not as a normal crossings divisor. That's why one decides to blow up once more this green point, introducing a curve E2. And now you see that the street transform and the previous curves form a normal crossing divisor. And by definition, to get an embedded resolution means that when we take the total preimage, that theoretical preimage of the curve, what we get at the end is a normal crossing divisor. So you see that here the minimal embedded resolution of the cusp, or how it is called since the times of Newton at least, the semi-cubical parabola, is resolved by a process of 3 blowups. Now let's concentrate again on this process and look at the final result. One represents the topology of the final result using a dual graph in which each curve is represented by a point, and when two curves intersect, the points are joined. So for instance here, you see that the street transform of the initial curve is this point here. It intersects the green curve here. So one joins the green point with this kind of yellow point. And now the green one intersects the blue curve. That's why we have a segment here. And one has to keep track of the other charts too, to see that the green curve intersects the red curve, which is not visible here. It's at infinity from the viewpoint of this chart. So this is a global picture on the resulting total surface, and the dual graph is this one. But to encode the topology of the curve, those curves are compact. And being compact inside a smooth surface, they have self-intersection numbers. And one indicates also those self-intersection numbers, and there are these 3 numbers here, -3, -1, -2. If one keeps track of this process, it's very easy to compute them, because when one blows up the red point, one introduces a curve of self-intersection -1. Then each time one blows up a smooth point on a curve, the self-intersection number drops by 1. So one blows up on the red curve 1 point, and again 1 point. So one has to drop -1 twice, so that's why one gets -3 here. The final curve appeared has self-intersection -1, and on the blue one, we blew up once more. That's why it gets -2. So in this way, looking at the whole process, we get these numbers. This shows that the dual graph is something which depends only on the final stage. So you can say the topological description of the final stage, but the concrete computation of the numbers is something which depends on the history which leads to the final stage. And this is important. You see that here inside we have both space and time. Time being this process of blow-ups. So here we are in the present, and this is the past. And you will see that lattices precisely allow to look at the same time at space and time. So now I come with a second answer. I told you initially that one of the methods to analyze singularities is to blow up till one reaches an embedded resolution. Now I will present the second main tool for analyzing them is to use Newton-Tweezer series. So this was a great invention of Newton. Newton made a powerful analogy which should be taught in the schools. But it is not taught, and I don't understand why, because I think more importantly than any method or any algorithm is the philosophy of maths. And a good part of the philosophy of maths is that to trust analogies and work hard to develop them. And Newton saw that writing decimal numbers with an infinite number of digits is a very important tool for doing numerical computations. And he said that analogously, when one has literal computations with letters, one could try to find solutions by an analog of infinite decimal expansion, in which simply one replaces 1/10 by x. And it is exactly what he did for such equations. If you want to solve f of xy equals 0, we look at it by making a break of symmetry. We look at this as an equation in the unknown y, in which x is given. And then we try to express y in terms of x. I don't say in function of x, because functions still did not exist in the year 1660s. But in terms of x, this was a way of looking. And the analogy says that one allows powers of x. And this is Newton's method. I will present it on this example of a series which is in fact a polynomial in the variables x and y, which is drawn here. And we look for a solution y, which is a series in powers of x. And this series then will be computed iteratively. First, we look for its first term. So this first term contains a constant and a power. First, we will look at the exponent, nu here. And then, in a second time, after having found potential exponent, we look at the way to find the coefficient. So, now simply we take this equation and we replace it in the given one. So you see each monomial, if you expand, here becomes this. So y to the power 5 is cx nu plus other terms to the power 5, minus 4 times x cubed y cubed is this one, etc. Now expand and develop, and look only at the initial terms of this series. And in these initial terms, I emphasize the exponent. Here we get 5 nu from y5, here 3 plus 3 nu from this one, 7 plus 2 nu from this one, and 10 from this one. And now comes the main observation. If we want this equality to be true, given that we look for a constant coefficient which is non-zero, well, it means that necessarily, if you look at these exponents, the minimum of the exponents is achieved at least twice. Otherwise, it would appear only once, say here, and this term could not be eliminated with any other term. So in some sense, this is the birth of Newton polygons, also of Newton-Puiseux series, but also this is the most important fact of valuation theory. This is in fact a property of arbitrary valuations. So in this observation, you have in a germ Newton polyhedra, tropical geometry, valuation theory. And in a sense, only after 2000, the mathematical community began to develop systematically this by looking carefully at the links between these things. So in this initial computation of Newton, it's interesting that you have the germ of something which develops in a very strong way only after 2000, the year 2000. So now let us re-express this fact that this minimum is achieved at least twice in a different way. What's my aim here is to show you how you arrive naturally to Newton polygons. And I say it mainly for young people in the audience because my experience as a student is that in the majority of texts, Newton polyhedra are postulated as God-given. And no, they were not given to Moses on a mountain. They came in a flow. And I try here to show you the flow of thinking which leads you naturally to them. So let's look again at our polynomial here. And I emphasize now the exponents in blue. And now remember that I represented the unknown exponent nu in red. So just rewrite the 4 numbers whose minimum we look for as these scalar products. They are the usual scalar products of vectors with 2 components. So say, look at this one, 3 plus 3 nu is simply the scalar product of 1 nu and 3, 3. And 1 nu and 7, 2, the scalar product is 7 plus 2 times nu. The general linear form here is this one. AB goes to 1 nu scalar AB. So this means that what we look for is that This linear form achieves its minimum on this set of 4 vectors. And these vectors are exactly the vectors of exponents of the monomials appearing in F. These are called the support of F. So the previous minimization problem can be re-expressed in this way. A certain linear form achieves its minimum at least twice on the support of F. And this is what leads to the operation of convex hull. In general, imagine you have in a plane a finite set of points, and you come with a linear form, non-zero linear form like here. And you want to see where it achieves its minimum on that finite set. Well, look at all possible subsets where it achieves the minimum when the linear form changes. What we get there is exactly the parts of the finite set which are inside the edges of its convex hull. One is led to introduce convex hulls of points in algebraic geometry precisely there. And in higher dimensions, in this way, you build what are called Newton polynomials. They should not be postulated in books. One should explain this process, which leads to them, it is impossible to escape their introduction because they appear in this way. In our context, we do not take the whole convex hull, which in my example here would be a parallelogram. You see that there is a missing point here. One is interested only in these two. Why? Because remember, we looked for the exponent nu as a positive number. This means that the kernel of the convex hull, of the linear form which we are looking at, passes through the origin in this way. It does not cross this quadrant. It passes like this, and then the linear form increases in this direction. So you have to imagine that you come with a line here, and then you move it parallelly, and then it increases. So the minimum will be obtained when it touches first this set of points. But because it increases in this way, it never reaches this point. That's why when we look at singularities at germs of curves and not at the global plane curves defined by that polynomial equation, one does not look at the global convex hull, but at a local version in which one gets only these two sides, and this is continued by parts of the edges of the first quadrant. So the local Newton polygon is a non-compact polygon which goes to infinity in this direction. It is the yellow part in my drawing. And now if we want the minimum to be achieved at least twice, in our case, well, we have only two possibilities. Either it is achieved here, or it is achieved on this edge. So we have two edges, K1 and K2. And then, if we compute the corresponding exponent, it's very easy on the drawing. Just look at this edge as a hypotenuse of a right-angled triangle, which is here, and compute its integral length. So you see here 3 segments, and here 2 segments. We get 3 over 2, and this is the corresponding value of the exponent. And here, you look at this other triangle, you have 3 and 7, and we get the quotient 7 over 3. So this gives us the possible initial exponents. And now we can turn to the problem of finding the initial coefficients. So that's why I emphasize now with the blue the initial coefficients. And now assume we are in the first case, that the minimum is achieved here. So it means that if we want this equation to be true, we look at the terms with minimal exponent. And we know that there are those corresponding with these 2 points. So with these 2 terms. This means that the sum of these 2 terms must vanish. And this leads to the equation C5 minus 4C cubed equals 0. Similarly, if the minimum is achieved on K2, then the terms involved are this one and the last one, and we are led to the equation minus 4C cubed plus 4 is equal to 0. You notice that this term will never contribute. And you see it here because it is not on this compact part of the boundary of the Newton polygon. So let's look now at these equations. Remember that what we want is number c which is non-zero. That's why we can simplify by c cubed here, which leads us to the equation c squared minus 4 equals 0. And here simply we simplify by 4 and we are led to this equation. In this example, notice that these two equations have simple roots. This is a sign, this is the algebraical way to see that we are in what is called in the modern language since the 70s, in the Newton non-degenerate case. And if we are in a Newton non-degenerate case, then the relation between these Newton-Puiseux computations and resolution by blowouts is the easiest. This means that the singularity in fact can be resolved in one step by only one toric morphism. And I want to explain this. So Newton non-degenerate, you see that it can be seen on the equations. Notice that to determine if a polynomial, a concrete polynomial equation here has only simple roots is computable by hand, because it's simply computing the greatest common divisor, which is the derivative. It does not involve in any way approximations of roots. And by the way, when Newton introduced his method, at the same time he explained how to compute approximately roots of numerical polynomial equations like this. And it is this method which afterwards, in the 18th century, was re-expressed geometrically as a tangent method. But Newton expressed it completely parallelly with the process which I showed you before. So now what I want to show you is how to resolve this by one toric morphism. But first, let's drop a little our concentration. I will show you some historical images. This is perhaps the first printed Newton polygon in his book, which appeared only after his death in 1736, The Method of Fluxions and Infinite Series. So you see already in the title, infinite series were prominent. And fluxions were his way of speaking about derivatives. For him, the functions were fluents because he was thinking physically that functions appeared as things which evolve in time, which they're flu, like water, and they change. And the fluxions were the way to measure the change of things which flew in time. So it's a very Heraclitean view of the universe. And you see that in this drawing, what he marked were not points, but he marked stars in two small squares. And since then, during a long time, at least till the 20th century, one finds the two traditions. Either marking points and then doing convex halves, or having a checkerboard and then coming with a ruler till it touches several squares which have stars inside, like here. So here you see that the minimum is in fact achieved 3 times. Yes or no, it's a problem for you to detect. So why do I ask, is it the first printed Newton polygon? Because around him he explained methods to his friends, and in fact I have no idea if somebody else did not print it in another book. For instance, Maclaurin, in the time of Newton, gave the first proofs of the classification of cubics by Newton. Newton only published results without any proof. So perhaps in the same way, somebody printed this somewhere else, but this I don't know. If some of you know if before this book somebody printed a Newton polygon, I would be very happy to know. Next image. Well, the initial image had only one edge. A little later, in 1750, Cramer, in his Introduction à l'analyse des lignes courbes algébriques, drew several Newton polygons, and here you see an example with 2 edges. And you see that there you find stars, but those stars are simply a way to make clear the support of a function. The other integral points are represented as points. And you see that the first quadrant is not oriented as nowadays. So you find till the 20th century a lot of ways of orienting the first quadrant. And Newton polygons were used for many things, and in particular for drawing curves by hands. And this is something which I find a lovely book, first published in 1872. Percival Frost wrote an elementary treatise on curve tracing. A book whose aim only to teach students how to draw the curve corresponding to a given polynomial equation. And there, drawing the Newton polygon of the given polynomial equation was an essential tool. So that's why here on this page, you see both here, you see as in the Newton time, a checkerboard and with monomials written inside the little squares, a different orientation, like here, and then also the point representation and convex hulls and things like this. And this he uses in order then to arrive at the global pictures of curves. And he makes both local studies near singularities, like here, and studies at infinity to be able to draw the asymptotes and what the infinite branches do. Some of them go to infinity without asymptotes, as you know, with the usual parameter. So let's come back to the main story. Now the question is how to get the dual graph of the minimal embedded resolution from the Newton polygon. Well, as I told you, the answer is simple in the Newton non-degenerate case. We have simply to look at the lateral boundary of the associated lattice. So this is the occasion to show you a special kind of lattice which is less complicated than the one I showed you first. Come back to our example. So now I got rid of all the letters here. I keep only directions of x and y. And here we have these two edges. Now we first construct what is called the dual fan. So please notice that here we have three objects: Newton polygon, dual fan, and associated lattice. In the title, they are placed in the same way as in the picture. So this is easy for you to see who is who. So here, simply imagine that you draw the two normals to the edges and the interior normals which get inside the Newton polygon. There are these two half-lines. So they correspond to these two edges. That's why I draw this in blue as this edge. It's the normal to this blue edge. And this green is the normal to the green edge. And you see that I colored also the regions between them. For instance, this violet region is between this green normal and this vertical one. So the green normal is normal here, the vertical one is normal to this horizontal edge of the Newton polygon. And simply look here at this vertex, and you look at all the intermediate vectors which are between them. So what does this have to do with the previous process? These normals has to be thought as the gradients of the linear forms. And you ask for a linear form, where does it achieve its minimum? So if you are strictly inside this cone here, when you arrive like this, the minimum will be achieved on this vertex. That's why this cone here is the dual of this vertex, because it indicates for which linear form the minimum is here. Only in this direction the minimum is achieved on this edge. Then in this intermediate region the minimum will be achieved only on this edge. Then here it's achieved here, and then in the final here pink magenta region the minimum is achieved only here. So that's why one has a perfect duality between all the cones here and all the edges here, the parts of the compact part of the Newton polygon. This object here is called a fan because it's similar a little to this famous Spanish object which is essential in the Spanish summers and nowadays also in the springs. So now here I show you how to pass from the dual fan to the lattice. Simply look at these two rays, and on each ray look at the first integral point. So you see here it does not pass through these integral points till it arrives here, until it arrives here. these 2 points have coordinates 2, 3 and 7, 3. And then the quotients 3 over 2 and 7 over 3 are simply the slopes of these half lines. So here I call P of 3 over 2 because it is the representing point of the rational number 3 over 2. And this is the representing point of 7 over 3. And instead of drawing these half lines, one draws, in fact, here a polygon, which is non-complex, which has as an edge the edge joining the bases of this quadrant. E1 and E2 are the generators of the integral points in this quadrant. Then one has a triangle here, and then you see that the triangle, one of its edges is extended by the same length, building a second triangle. And here this one is extended, a third one, and a third one, and like this you get a sequence of triangles which arrive at these 2 points. I will explain you in a little moment more precisely how you do this in general, but now you see that we enter inside the structure of this lotus. This particular kind of lotus is, in fact, a simplicial complex made up of triangles. So it is a triangulated surface. Topologically, this surface is a disk. And if you look at the way the triangulation is done, you see that you do not have vertices in the interior. So it is triangulated by diagonals. So let's advance. This object is already interesting in itself as a simplicial complex, but with a little decoration. One has to keep in mind this initial segment, which is the seed of the growth, and this initial segment is oriented. Why? In order to know which is the first vector and which is the second one. This is what allows you to transform the pair of numbers 3, 2 in a rational number, and to differentiate 3 over 2 and 2 over 3. So this initial orientation is what allows you to discriminate between a positive rational and its inverse. So what is a Newton lotus? A Newton lotus is something which you get naturally from a Newton polygon. It is a diagonally triangulated disk with an oriented base, this one, and marked vertices, these 2. Why marked? Because we keep in memory the compact sides of the Newton polygon, which were transformed into the 2 rays, which have 2 slopes. And those 2 slopes allowed to construct this object. So they are here. And now you see that this abstract simplicial complex has this canonical embedding in the positive quadrant, R2 with positive coordinates. And here in this page you see the definition of Newton lotus. It is exactly something like this. And given a finite set of rational numbers, that is, given any local Newton polygon, you get an associated Newton lotus. Are there questions? Yes?
You say canonical embedding, but so there are no such things. So how do you choose, for example,
Because of the rule, very good question, thank you, of the rule I explained you before. Here we have this initial triangle, and then each time, if you go to the left, simply you extend this edge by an equal 1. And here this one is extended by an equal 1. And here by an equal 1. So here the geometry is purely affine, not Euclidean. So angles don't matter. You have to simply think about extensions of segments. So now this abstract lotus allows to read the final divisor of the minimal embedded resolution. In which way? Well, simply look at its lateral boundary here. Lateral means that we do not count here the base inside it. So you see that it is a polygonal line. And now at each vertex we count the triangles arriving there. 1, 2, 3, and we write -3. Here only 1, we put -1. Here there are 5, -5. And we continue in this way. And when you extract this line and you make it straight, well, I make it straight only from here to here, because these two extremities represent, in fact, the initial axes of coordinates, which are the zero loci of x and y. And that's why I represent them as these arrowhead vertices. And there, where we have the vertices given by the sides of the Newton polygon, here we put one arrow each time. Why one arrow? This is not universally true, but I will come back here to show you something. If you look at the edges, everything here in the construction of the lotus depended on these two rays. But I said that this is a dual picture. But this is not true duality like in projective geometry. True duality would be something which is involuntary. If you apply it twice, you get back to the initial object. Here you have an infinite number of Newton polygons which lead to this. Imagine simply that you make a homopathy here. This is in fact the simplest Newton polygon which leads to these two rays. In which way, if you look here at the compact edges, you will see that you have no integral points inside. So here you have only the extremities which are integral and nothing inside. That's why we have only one arrow, because the integral lengths of these segments are 1. And this is the way we know how many arrows to put. If we had, for instance, integral length 5, we should have put 5 arrows. So let me speak now about a little toric geometry. I told you that the lotus allows to describe the dual graph of the minimal embedded resolution. But that is in fact a jump I made. First, we have to understand that a fan, and now I take a little more complicated one, because I want to show you a more complicated process which is not Newton non-degenerate. Because of the property I just told you, that the sides had integral lengths 1, there we could have only Newton non-degeneracy. Here I will tell you something more complicated, which is not Newton non-degenerate, in order to lead you to the general definition of a lotus. So here I start from a fan with 3 rays. You can look at the corresponding coordinates, but it's not important. Just look at this configuration. And I call the rays rho 1, rho 2, and rho 3 here. Now remember that in the construction, this initial segment was crucial. It was the base of the future lotus. And just draw it, and now intersect the rays with this segment. We get 3 points here. It is what I represent here magnified. So you see these extremities here, I told you that they represent in fact the axis of coordinates. From this moment on, I will call the axis of coordinates, so this is defined by x equals 0 and this by y equals 0, I will call them by L and L prime. Toric geometry tells you that this drawing allows you to define a more general kind of blow-up of C2. A blow-up which replaces the origin not by one curve, as in the usual blow-up, but here by 3 curves, which correspond to these 3 directions here, the intermediate ones to these 3 points. And now, when we do this, we get a new surface. And if on this new surface we draw the total transform, the total pre-image of the axis of coordinates on C2, we get this curve here. So the 2 initial axes of coordinates are separated and they are interpolated by this chain of 3 curves. Chains of 3 curves which correspond to these 3 points. So you see that the dual graph of this toric modification dictated by the Newton fan can be read here in this picture. Just draw the base of the lotus and then intersect it with the rays. Okay? So this is something which is very concrete, is for drawing. When you have Newton polygons, you just have to draw this, and you know that you access in this way a special kind of dual graph. This dual graph is not on the surface of the minimal embedded resolution, because this surface in general has singularities. So here one has to resolve the singularities of this surface. And I will show you in a moment how to determine where they are and their internal structures. But what is this special transform? So look again, you have F. F gives you a Newton polygon, and the Newton polygon, through its dual fan, leads to a toric morphism. So God-given. So it says, my function wants its ambient surface to be modified in this way. He says, don't blow up stupidly a point. No, I want to be changed in this way. Why? Remember with the cusp, when we blew up stupidly the origin, the strict transform passed again through the origin. And again through the origin, in the toric context, means that it passed through a torus fixed point. To do toric geometry means that here we are in ambience when we don't have only static surfaces. We have a dynamics here. There is a commutative group, just C star to the square acting on them, and the surface is decomposed into orbits. And the orbits of dimension 0 are simply the fixed points of the action. On the initial plane C2, the origin is the only fixed point. So when you do that process and you create new charts with new origins, those are the fixed points. This toric modification is the minimal one in which the strict transform of the curve does not pass anymore through one of those fixed points. This is its geometrical meaning. So you see the equation God-given tells you how to get rid of the fact that you pass through the origin. And therefore this dual picture here allows you to see the dual graph of Z transform. And now we broke up the problem of drawing the dual graph of the minimal embedded resolution into two steps. The first step which constructs this intermediate dual graph, and now a second step which will enrich it by resolving the singularities of this. And in this way you see that we broke it up, we separated the problem from the curve, because now we have singularities outside of the strict transform. So it's a separation of problems. It's really like in resolution of singularities, which does not mean to find an equation. It's resolution in the sense that things which before were one are separated into pieces, like the resolving power of an instrument of astronomy. Where we saw a star, there is a galaxy. Here is the same. The initial process is broken into two separate things. So now I want to show you that how to think geometrically about all the computations which are done when one resolves singularities by this process of using Newton polygons. There are a lot of computations, and it's good to have a simple mental image behind those computations. So here, a very important object which allows to follow everything is simply a cross. So we call a cross something like a normal crossing divisor. A normal crossing divisor on a smooth surface is simply a collection of smooth curves which intersect transversely. So what you see at each point is something like this. But a cross is simply an ordered set of smooth germs which intersect transversely. So here we have the order L and L prime. And this order is crucial for the problem I told you before, that in the quadrant we have to say which is the first vector and which is the second one in order to discriminate between a rational number and its inverse. So in the crosses we have always the first curve and the second curve. And now, in order to think geometrically, we have first to think about the meaning of Newton polygon. Its definition depends on the initial function. So let's see, it depends on what objects geometrically. Well, the first important fact is that the Newton polygon and automatically its dual fan depend only on the cross defined by the coordinates and on the plane curve singularity C defined by F. So it means that Newton polygon you have to have in mind each time you see a cross somewhere, so it can be a global curve with normal crossings, and you have another curve which has a singular point at a cross of this global curve. Without any need of fixing coordinates, there you have a Newton polygon. And so it's very important to know that you have a Newton polygon, therefore a dual fan, therefore a toric modification, but also that toric modification from the viewpoint of analytic geometry does not depend on the coordinates. It depends only on the cross. So that toric modification gives you in fact a canonical toroidal modification. So now each time you see at a cross some curve, I did not draw it because initially before the analysis we do not see it. So you just have to know it is there. Like when you go in a forest for mushrooms, initially you don't see them. So they are there, it's our problem to see them. But you have to know that what we get at initially is that toroidal modification. So we have to agree on this. This is a geometrical interpretation. We need a cross and a germ of curve. Then we have a Newton polygon, a dual fan, and a toroidal modification. And now comes the very important question: what to do if F is not Newton non-degenerate? We would like to do as before, to reach an embedded resolution and to read the dual graph. How to do it? Well, simply iterating what we did before. Newton told us to iterate, we keep iterating. So I put here a reference. Starting from the 90s, Mutsuo Oka had in collaboration several papers where he developed this strategy of resolution and computing invariance through iterations of Newton modifications. And then other people contributed to this direction. In our article in the handbook, we tried to say as much as possible which are the relevant words, but also in the introduction, we say that we are not conscious of everything, and we hope that people won't be our enemies if we forgot them. So please simply tell us about references which we forgot, because the literature is in fact very immense around all these problems. So for historical details, each chapter of our text has a final section of historical remarks. So if you are interested in that, you could look at it. So here, this is the page of my Beamer, which is has the biggest amount of words. And I say to my students not to do this. Well, simply I did not want to break the algorithm. Let's read it together, and then I will show you through pictures what we do. But seeing words allows to get conscious of several important aspects of this algorithm. So first, we start from a smooth germ of surface. I told you that I want to express things geometrically now, so I won't speak anymore about F. I will speak about a germ of curve C. We are on a smooth germ of surface. On it, L is a smooth branch, and C a reduced germ of curve, which does not contain the branch L. So you see, I don't fix a cross. Why? Because the first step of the algorithm tells how to stop. If L and C form a cross, then we stop. Each time you arrive at a cross, the algorithm stops. Otherwise, so we have L, which is smooth, and C, which can be like for a semi-cubical parabola. You could have a smooth curve, but which is tangent to L. So it is not a cross. So that what we do is we complete L into a cross. And now we have a cross and we have C, therefore there is a Newton polygon, an associated Newton fan, and an associated toroidal modification performing. So the new surface S is replaced by a new one, S tilde, in which we look at the strict transform of C. The new one can have singularities. We just saw an example. But now you know that the strict transform does not pass through them. It means that it passes only through smooth points of the exceptional divisor. So there you see again the initial situation. And there you understand why the initial situation contains only one smooth curve and not a cross. Because there you have only one smooth curve, the germ of the exceptional divisor, and the strict transform. And now you repeat. Step 4, the new surface is the toroidal modification. And now O is any point of the strict transform, so we will have to repeat for each one of the points of the strict transform. L will be the germ of the exceptional divisor, and the new curve C is the germ of the strict transform there. And then go up to step 1 and continue. And you see here that I said choose, which means that this algorithm is non-deterministic. It involves choices. And second, for each point. This means that at each step one has to run the first part of the algorithm several times. And this is a ramification process. And that's why we have trees behind. Each time in an algorithm you have to repeat the same step several times, we have trees. So let's see now concretely on an example what happens. I start now with this a fan which I showed you with the 3 rays. Here I also draw near each one of them the corresponding slope. For the moment it's not important. You just forget it. And here it is that I wrote the notation. Why it is important? Because you see that now the fan is a fan of the germ with respect to the cross LL1. And it's important here to see in each fan on what it depends. It depends only on this object, geometrically. So you see, this is the initial cross. Here I don't know how is my curve. The curve tells modify the surface in some way. Okay, I do it. She wants to modify it in this way. I listen to it and I modify it. And now you see that you separate Ln and L1 using these 3 curves, which correspond to these 3 rays. And now for each one of them, one can compute concretely to see if one gets simple roots or not. And if you get a simple root for the intersection with the exceptional divisor, this means that in fact the germs there were smooth and transversal to it. If it is tangent or singular, then you get a multiple root. So simple root is in fact the sign that there you stop. So if we stop, we know that we have there a smooth germ which appears like this. So that's why you begin to see the branches of the curve appear. We know already that we have 3 of them. But here I draw 2 more points where we have multiple roots. So there we have to repeat the algorithm, so it means that there we need a cross. Here you see only the exceptional divisor, so just add smooth branches transversal, which allow to repeat this algorithm. This is what I do here. So you see, we add L2 and L3 through those points. At each one of these points appears a new Newton polygon, therefore a new fan. Say, for instance, that we get these 2 fans. Here you see that it is a fan of C, but relative to these 2 curves, E1 here and L2. That's why we have this is E1 and L2. And here it is relative to E1 and L3. Okay, so we do the corresponding modifications. Each time we have 2 rays, which means that now we separate the curves, introducing 2 new curves here. Each time the new curves, I represent them in red, so you can concentrate on them. And assume that now you discover that you have 3 more branches here. But there is a remaining point where we have a multiple root. So we have to apply a 3rd time the algorithm. So we were on the 2nd stage, now it's the 3rd stage here. And assume that the last time we have only 1 ray. So here one ray with respect to a new smooth germ which makes a cross appear. And then here we separate them using one red one and assume that now everything is smooth. We reach here a situation in which you have a normal crossing divisor in the neighborhood of the street transform of the curve. You see that there it intersects transversely the exceptional divisor. But the ambient surface has several singular points. In this example, it turns out that there are these ones. So the big blue points should be resolved if you want to reach an embedded resolution in the usual sense with a smooth ambient surface. By the way, expressing things geometrically has the advantage to adapt to any user, because how to choose this supplementary branch here for making a cross? You can work with charts like initially, but then this can be seen in two charts. And then you can choose in one of those charts to translate an axis of coordinates. But it turns out that if you translate in the other chart, you do not get the same curve. So you have already there different possibilities for this choice. Or you could also say, well, I have there some curve, it has several branches, I can choose a smooth curve of maximal contact. Some people do that. They try to put there a smooth curve with maximal contact with a given one. So there are several possibilities. This is something, a geometric way of understanding them all. How to choose to do these things depends on your problem. And the final object will not be an invariant of the given singularity. It will be an invariant of the given singularity and of all these blue curves added through the process. Added to form what? Crosses. So they are ancillary. People don't see that there are those which prepare the lights here and the sound, but they are essential for the whole process. And at the end you will see that the initial curve comes also with all of them. So I thank all the people here who make me understandable by you, because they are like those curves. Without them, we could not understand what happens. So you see, the moral is, you do computations with coordinates, you have several coordinate systems, each time you have to add the axis of coordinates. Don't forget the axis of coordinates. This is a very important moral in the study of topology. So, how to get the dual graph of the final divisor? By constructing the fan tree of the pseudo-resolution. So I want to explain now this. Please let me drink a little. And please dream how you would answer this question. So we continue with the previous example. We start again. Remember that we had a process in which we had 3 stages of buildings of Newton fans. This is the first one with 3 rays. Do the construction I showed you first. We draw this segment and we intersect it with the 3 rays. We get this yellow segment and we get these points. And now decorate these points by the slopes of these rays. So you see that this segment with these decorations encodes completely this geometry. So this is what we call the trunk of the first Newton modification, or of the first Newton fan. The situation seems complicated, but in it you see all the actors. The curve you want to analyze and the cross used to analyze. And you see that L and L1 appear now at the extremities of this segment. And this is crucial. You have to have these names also, and E1, E2, E3 are the exceptional divisors which appear by this first toroidal modification. And what is important there are those names. Why? We will see in a moment. Then for the next stages we do the same. So believe it is what we do here. The third one, the same. But you see each time we are careful to draw the names near the points. And at the end, when we stop, we have many points where we stop. It is there where we see the trig transforms of the branches of the initial curve. It is only at that moment that, for instance, we know how many branches it had, something which we did not know initially. So there, we have a curve which is part of the cross. So if it is part of the cross, well, its corresponding Newton polygon has no compact edge, it's only a vertex. So the dual fan has no new ray. So then you get the empty segment without subdividing it. So that's why we have as many empty segments as the initial curve has branches. Okay? And now let's summarize. We got several trunks. This is the first appearing one. These two appeared in the second step, and in the final step, this one. And then we have all the segments corresponding to the stopping situations. But you see, each point has a name. Either a curve which was added, which are these light blue ones, or the initial one, L, or the exceptional divisors at which we added the new blue, light blue ones. And in red here you have the components of the exceptional divisor. So what we do now, we glue. How? By identifying the points with the same label. So you see here that this segment here, you see it in this vertical segment. L, E1, E2, E3, L1. It's this one. But here you see that you have E1 a second time here. So it means that this second segment should be glued to this one at E1. So you see it here. E1, E4, E5, E8. It's this one. But E1 appears also in the third one. So the third one also should be glued here. So you have E1, E6, E7, L3, which is here. This one, E6, E8, E4, is glued at the E6 point. So here. And then you come with the final ones, which are added everywhere here. So this is the fan tree of the Newton process. Each Newton polygon has a dual fan, which is encoded by a trunk. You glue all the trunks and you get a tree. And now you see that in this tree, you have, in fact, it's not a purely topological object seen in this way, but also you have to remember like maximal geodesics. This one, and this one, this one, and this one. These were the non-trivial Newton polygons of the process. We had 4, so that's why we have these 4 big segments. So, now if you add the information we had the information of the slopes. So each point comes with a slope. So here we have to think about this as a function which grows continuously from 0 to infinity along this segment. And here it reaches 3 over 5. And on this second segment, again it grows from 0 to infinity. So in this way, you see that forgetting that this goes straight, this function allows to see where it goes straight. In this direction, the function is continuous, and here it has a discontinuity. It jumps from 3 over 5 to 0 again, and then it grows again to infinity. So here you have to see this as we have this tree endowed with a function with values in 0, infinity, and this function has maximal regions of continuity. And those maximal regions of continuity are in bijections with the crosses where we made Newton polygons. So this is in fact the fan tree and the numerical information which is needed if now we want to answer our question how to get at the dual graph. So just before arriving there, I told you that to get at the dual graph, we have to pass first to the dual graph of the corresponding toroidal modification, and that has some singular points. Before, you believed me or not that those were the singular points. Now I show you how to compute it. Now, on the fan tree, well, you have these decorations. We know that this fan tree is, in fact, the dual graph of the final divisor. It is this what we got by construction. So here you see exactly each vertex represents one of the curves. So each intersection point here represents is represented by a segment between two vertices. Assume that I concentrate on this light blue point here. I want to know, is it singular or not on the surface? It corresponds to this segment here. I look at the corresponding numbers, 5 over 3 and 3 over 1. I build a square matrix with them, and I compute its determinant. It's -4. So the metric is not unimodular. This means that that point is singular. So in this way, by looking for each segment at the corresponding determinant, we see if the point is singular or not. For instance, here, 2 over 3 and 3 over 4, 2 times 4, 8, 3 times 3, 9, 8 minus 9 is -1, so there you have a smooth point. That's why this is not represented in blue, it's not a singular point. So now we know that our task is to resolve all those singularities. Those are very special types of singularities. They are singularities of toric surfaces. And they always can be resolved by a segment. So concretely, it will mean that here we have to subdivide the blue edges using some points and then putting self-intersection numbers which are negative. How to do that? Well, first is do what I just said to you, how to get an embedded resolution by resolving those toric singularities. But how to read the combinatorial structure of that embedded resolution from the Newton polygons? By constructing a lotus from the fan tree. So the lotus appears precisely at this moment when we want to resolve the singularities of the ambient toric surface. By the way, it can appear in other ways. What I tell you is the story which we tell in that chapter. But then we can introduce it in different ways. So let's come back to the initial kind of example, to Newton lotuses. Come back to the fan with 3 rays. And the fact that the corresponding toric surface was not smooth came simply from the fact that this fan is not regular. Meaning that, for instance, if you look at this cone here, and you look at the primitive generators of its edges, these 2 points, if you join them, you form here a triangle, and inside the triangle you have more integral points than the vertices. You have this one here. And if you do the same here, you see that you have 3 more points, and also the same. So that's why we have singularities. So the way to get a resolution is simply to get a finer fan by regularizing this one. How is this done? By the following process. Look at all the integral points inside the cone, except the origin, and take their convex hull. So we get here this compact polygonal line. In the second one, the same. We do this convex hull and the convex hull here. So you see that you get here this polygonal line, which is a union of the boundaries of the convex hulls. And now we will look differently at this. You see that the interior here has a rays inside. And the new ones, which regularize the fan, are simply joining the origin to the new points, which are added here. Well, erase that part and draw something else. So you erase this, and now you see that inside you have these triangles. What happens there? We start from the initial triangle, which we call the initial petal. Petal because what we build are lotuses. And lotuses are not built out of triangles, but out of petals. So initial one here. And then you see that it is generated by the vectors E1 and E2. And the new vertex here is E1 plus E2, the sum. Now we can repeat with the 2 new edges. And if we draw the corresponding petal, we get these two new triangles, so 2 new petals, which correspond to these new vectors in the first quadrant, which form, again, a basis of the ambient lattice. And now, you see the rule I told before. This segment is prolongated with an equal segment, and here with an equal segment. So what's the meaning of this? That each petal represents a blow-up of the center of a cross. Its base is a starting dual graph. So in my examples, we had the axis of coordinates, two axes. The dual graph is a second. It is a base here. And the arrow tells which is the first curve of the cross and which is the second one. When you blow up, you create a new curve here. And the initial ones were separated. So now they intersect through the new one. So the new dual graph is the blue one. So you see here that this triangle allows to see the transition from one dual graph to the other one. It's an elementary space-time, showing how evolved dual graphs during the blow-up. And then you iterate. And I show you the part of the universal lotus, if you iterate indefinitely, the part contained in the square times 10 times time. And it is this kind of drawing which made us introduce the term lotus. So the initial petal is here, and then you keep constructing petals. In this way, one reaches exactly the primitive vectors in N2. So the vertices you get here are exactly the vectors whose coordinates are coprime. Again, some images, and I was told to stop at 10:30, so I will stop after these historical images. Afterwards, after I made the first article introducing lotuses in 2011, I discovered that prototypes of these drawings appeared before. For instance, in a paper by Duval of 1944, but where he was not thinking about curves, he was thinking about infinitely near singularities and the proximity relation between infinitely near singularities. And it turns out that if you join proximate points, well, you get, in fact, lotuses, as you see appearing here. And here you see clearly appearing part of the universal lotus in the same paper. So, well, you will see this tomorrow. Thank you very much for your attention. Well, Elia told me thank you for. So you can imagine what you want afterwards.
Okay, so that's my next one. Thank you very much, David, for this beautiful talk, this discussion. Thank you very much. So, but David, some question, remark, please. So, any question, remark?
So first, thank you very much for the nice talk. So one of the points is petals, like benefits solutions, may become very complicated from, and one of the points is you just forget to solve the Gaussian singularity. Maybe there are petals that also have the information.
I will speak tomorrow about all the information which you can see there.
Because in that way, okay, you could start from a curve in a toric singularity, and basically the idea is this is the starting point, but with your method, in the next blowing ups, the street transfers pass through smooth points, right?
Yeah, exactly.
So
Okay. Any other question, remark? If not, so I invite you to invited to the second part tomorrow at 9 o'clock. The second part of the lecture of Batik. We thank again the speaker. Thank you very much.
Espera un segundo. Espera.
In 5 minutes, at 10:40, we will have the opening ceremony here with 30 minutes and then we'll have the coffee break.
Pero no había pasado hasta que has movido. Es que las vacaciones están
Que estos días, en teoría, acaban a la 1, sí, ¿no? O sea, a la 1:30, y empiezan aquí a las 4:30, quitando hoy, que empiezan a las 4, y luego, en teoría, el miércoles no tiene que ir a la tarde, pero están mirando a ver si lo cambian del miércoles al jueves. Lo digo porque igual lo cambian porque estéis un poco prevenidos. Vale. Entonces, la idea yo creo que se va a cerrar aquí de 2 a 3:30 por ahí.
Pero ahora ya es el descanso.
Ah, no, ahora es la inauguración.
Vale, vale,
¿Vale?
vale.
Y luego se supone que después de la inauguración es el descanso.
Pero la inauguración a que se refiere.
¿De qué?
Una sesión de inauguración, ¿no?
Sí, sí, nada, estamos...
Claro, nosotros en el programa yo no se supone que ahora tenemos descanso hasta la siguiente ponencia.
Sí, sí. Yo creo que en principio la pone.
O sea, poner
to the first invited talk of this conference. Welcome to all, include Kike and Alex. And the first talk will be by Pierrette Caslouguès, de l'Université de Bordeaux. Le titre, c'est, vous voyez, elle va parler avec surtout de Newton tree ad infinitum.
First, I want to thank the organizers to give me, to ask me to give this talk in honor of my two young collaborators, Enrique and Alejandro. I met Enrique, I remember, in Geneva in 1990. And it's harder to say for Alejandro because he was a student in Madrid. I was visiting Madrid often, and I guess we met without meeting. But what I remember is that Nacho asked Alejandro to teach me how to use Maple and Singular, and I must say it was a difficult task for him. Then, over all those years, we wrote something like 15 articles together, and we never quarreled. And even more, we became friends, and I hope our collaboration will and our friendship will go on as long as possible. Then, today, I will speak about the structure of Newton trees at infinity. This is a common work, a joint work with Daniel Dale from the University of Ottawa, and it's a work in progress since years. Then, if you take a polynomial in two variables, then you can associate trees at infinity. You have many ways to do that, either a resolution of polynomial maps, topology, Newton algorithm, whatever you prefer. But I will not speak about going from polynomial to trees at infinity. I want only to study the trees at infinity and try to understand them, to find the structure in these trees. A priori, that seems quite complicated, but we can find structures in these trees. And the fact to find structures in these trees allow to build abstract trees. And another game is from these trees at infinity to find polynomials satisfying with these trees. To find some polynomials satisfying a tree, usually it's not that difficult, but to find all the polynomials, it's not that easy. Then, general definition, I will go quickly because you all know about those trees. I will, mostly my model are splice diagram used by Eisenberg and Neumann. These trees are decorated trees, and they are decorated with integers at the end of the edges. I will only consider rooted trees. That means that I have a special vertex called the root, which will be denoted by V0, and I will assume that V0 has valency greater or equal to 2. Using the root, we can define a partial order on the vertices and arrows by saying that V is less than V dash if and only if V is on the path between V0 and V dash. And then when I take an edge E, with vertices or arrows V and V dash, with V less than V dash, then I can define the near end of the edge and its far end. The near end is the end attached to the smallest vertex. When we take an edge between two vertices of valency greater or equal to 2, we can define its determinant. Then on the edge, we have the two decorations, Q and Q dash, and we have decoration outside the edge. That means on the edges incident to V and V dash, but not E. We take the product near V, the product near V dash, and the determinant is QQ dash minus BQ dash. And I will go directly to the drawing here. Then you see the determinant. And now if you take a vertex V and an arrow alpha, you can consider all the decoration adjacent to the path between V and alpha. And it gives you a number which is xv alpha, and you can define the multiplicity of a vertex to be the summation on all alpha of xv alpha. And then now I will give the main property of the twins that I will study. For each vertex V of valency greater or equal to 2, I assume that there exists an arrowhead such that alpha is greater than V. All decorations near the root are equal to 1. Then all near decorations, that means decoration on near ends, are greater or equal to 1, and near the vertex, at most 1 is strictly greater than 1. The decoration near the vertex are pairwise prime, and moreover, then all these properties are common for many trees, and now I specialize. I ask that for all edges between two vertices of valency greater or equal to 2, the determinant is negative. This is for trees at infinity. And also, I ask that for all vertices V, NV is greater or equals to 0. Then, now, if you think about polynomial, that means that I am studying the trees of generic fibers of a polynomial, not the special fibers, only the generic fibers. Then, an example of tree is this one, and I put in parentheses the computation on NV for each V, and you have the decoration on the edges prime to each other. This is the Briançon polynomial. Now, it can be proven for these trees that the set of vertices such that NV is greater than 0 is connected. That means you have a nest of the vertices with NV strictly greater than 0, and on each path between a vertex with NV strictly greater than 0 and an arrow, you have a vertex with NV equals 0. Sometimes this vertex, you don't see it because it's not drawn, but it exists. And Then you have a nest of the vertices greater than 0, and all around the vertices with NV equals 0. And such vertices with NV equals 0 are called the dicritical vertices, and they play a very important role in the theory. Then I took again the previous and I put in black the dicritical vertices, and you see you have here a dicritical vertex which is of valency 2, and it was not pointed out in the previous tree, but it exists. And from now on, when I draw a black vertices, it's a dicritical vertex. Okay, then now we define the multiplicity and the genus of a tree. Then the multiplicity of a tree will be defined by minus the summation of a v of nv times delta v minus 2, where delta v is the valency of v in T. And if you think about the generic curve of a polynomial, and it's 3 at infinity, actually m of t is equals to the Euler characteristic of v. This is a result from Neumann, and this Euler characteristic can be written by 2 minus 2, the genus of v, minus n, where n is the number of points of puncture of the curve, and that is the number of arrows of the tree. Then now we define the genus of the tree by 1/2 of 2 minus m of t minus n. This number m of t plus n can be proven to be even, and this is a natural number. Not a natural number, but an integer. Then two small remarks. I will not insist because it's not so important. Vertices of valency 2 can be ignored, except for the root and the dicriticals. And also, if you have this situation, v dash of valency 1 connected to a v with an edge decorated by a, then that means that the multiplicity of v dash is the multiplicity of v divided by a, and if a equals n equals 1, excuse me, then the two multiplicities are equal, and in the formula for m of t, they disappear. Then we can also ignore this situation here. But it's not very important. You ignore or not ignore, it doesn't matter. Okay, then now an example of a more complicated tree is this one. You see here, for example, we have a dicritical vertex of degree 126, and we have all around dicritical vertices. And now I didn't write anymore the decoration of the edges. I only kept the multiplicity of the vertices because it's what I will need in the following. Then you see the multiplicities of the vertices, and this black vertex with this, for example here, this black vertex with this arrow and 126 means that the dicritical vertex has 126 arrows attached to the it. And this number, the number of arrows, I called it the degree of the dicritical vertex. Then in this case, the multiplicity of the tree is minus 216. The number of arrows is 218, and the genus is 0. Then it becomes to be it becomes to be an interesting tree. Okay. Then now I will study the trees. Then the idea. First, I will study what happens around a vertex. Then I will study some paths in the trees, and then I will study the whole tree in 3 steps. Then first, I am studying around the vertex. Then we have 3 sets of vertices. The vertices with NV strictly positive and delta V greater or equal to 2, and the dicritical vertices, I recall NV equals 0, and the vertices with valency 1. Then I can put in the same set the D0 and D1, I call this set D, and if I take an element in this set D, if it is a dicritical vertex, I define by du the degree of the dicritical vertex, and if it is a vertex of valency 1, I declare du the multiplicity of u. Then we have this set D and the set of du's. Then now I say I want to study around vertex V in N. Then I denote by dV the set of U in D adjacent to V, connected to V by NH. And first, what we can prove, it's quite easy, that we can prove that du divides NV for all U in DV. Then we have a set du dividing NV. And I put a double, I wrote this set as a multi-set. I mean, if I have 2 times the same number, I put it 2 times. It's a multi-set. And I consider the number delta of V, which is the sum of D in dV of NV minus D. Then this is positive of 0 plus epsilon V minus 2 times NV minus 1. Then now, epsilon V, I didn't say, but the set N of vertices of valency strictly positive is the subtree of T, and now I consider the valency of V in this subtree. Okay, and then now this number can be negative, then this number is an integer, but it's positive or negative. What is very interesting is that the sum of all V in N of delta V is equals 2 times the genus, which means that delta V actually is the contribution of my vertex V to the genus. Then I wrote again delta V here, and I have this small lemma, which is mostly obvious. If NV is strictly greater than 2, and its epsilon of V is strictly greater than 2, and NV is greater than 1, then delta V is strictly positive. If epsilon of V is equal to 2, and delta V was 0, that means all the D's are equal to NV, and if epsilon of V is equal to 1 and delta V is negative, then it's a small arithmetical property to see that at most one of the D's is strictly less than NV. Okay, then I am around the vertex V, and I study all the edges that stop at the first step, connect with arrows or vertex of valency 1 connected to. Then now I am interested in the edges connected to elements of N. Then, first of all, I define by D of V the GCD of all D's in DV, and I consider now pairs V, E, where V is in N and E is in an edge in N incident to V. And I denote by P the set of such pairs, and I can define a partial order on these pairs, saying that VE is less or equal to V dash E dash if and only if E dash is in the path between V dash and V, and E is not. Okay? And I will define them. You see, we have this, and now I will define by N of VE the set of all the U's in N, obtained if I cut my edge E. On E, I cut out a part of the tree, and NV is the set of U in this set. But if I do the same here, we have N of V dash E dash contains N of VE. Then, if I come back here, I defined the characteristic number of VE to be the GCD of D of U for U in N of VE. And if I have VE less or equal to V dash E dash, then C of V dash E dash divides C of VE. Then now, mostly is definition, and but proposition 2 is needs a little work, but again, now this C of VE divides NV. Then you see we have V, and all the edges around V, we have a number, an integer number, that divides the multiplicity of V. It's very beautiful. Okay, and these two facts are very interesting. The first one says that C of VE can be equals to NV only if the edge E is the edge going to the root. Then we have only one edge such that C of VE can be equals to NV. All the other edge, it will be smaller, strictly. Then now, thinking about that, you can ask, you can define what we call the number of V, which is the number of E's arising to V in T, such that either du is strictly less than NV, or C of VE is strictly less than NV, and this number is bounded by this, by the maximum of 3 and 2 times the genus plus 2. That means that because of property A, that means that the bifurcation in our tree is bounded by the genus. Okay, this, we come back to our tree. Then now I put the vertices. The black, in black I put their multiplicity, and in red you have the C of VE on the edges, and outside here, this is the DUs. Okay? And you see all the red numbers divide the corresponding multiplicity. Then, now I put a small interlude to speak about what I call Alexander-Dymka polynomial. I don't know if it is the good term, but okay, you should tell me. In his paper, Monodromy at Infinity for Polynomials in 2 Variables, Alexander Dymka decomposes the Alexander polynomial of the monodromy at infinity in 2 parts, T tilde and Ta tilde. And the operator Ta tilde, he says, is semi-simple, and its Alexander polynomial can be computed uniquely using the degrees of the dicritical vertices of the tree. And the other part, delta of T, this part has degree 2 times the genus. And the genus, which is the genus of the generic curve. And then it's this part that I call Alexander-Dymka polynomial, to say it's a part of the Alexander polynomial, and we can define a rational function. This is no more a polynomial, it is a rational function. Then for each v, we consider this, and you recognize that the degree of this rational function is exactly what I called before delta of v. And the product over all vertices of this rational function associated to v is the Alexander-Dymka polynomial, and it's of degree 2g. And now we can consider this rational function. We take the product over all elements in n of VE. We have a new rational function, and actually the degree of the denominators, and if we write it with 2 prime polynomials, the degree of the denominator is C of VE minus 1. Then this is an interpretation of our characteristic number. And moreover, if this degree is less or equal to 0, then this rational function is exactly this one. Okay. Then I stop here for this interlude, and I will come back to this at the end of the talk. Then now I will speak about small, not small, I will study simplified tree. That means it's not the same tree I will study trees with less D-critical. If you have less D-critical, it's not the same tree. But it's useful because they are simpler. You can classify them and you can come back to the developed trees. But many trees can have the same reduction. Okay, and then I will study reductions. And then I will not explain in detail the reduction. I just show you two examples. And if you consider a tree with a vertex V, and I assume you to have one D-critical vertex of degree D, which is a divisor of NV, and the other D-critical has degree exactly NV. Okay? If you have this situation, you can find a new tree where everything in the dotted part is the same as before, but now you have only one D-critical with degree D. That means you can find new numbers, a new combinatorics in that part to have this. Okay, then you can make D-criticals of degree NV attached to a vertex of multiplicity V. You can make them disappear. Okay, and the same here. You have this situation and a D-critical here of degree NV. And here your vertex is attached to a vertex of valency 1. Then you can make this vertex disappearing and make here a new D-critical of degree NV over A. That means you have less D-criticals of degree degree NV. Then, and you see in all our formula for the Alexander polynomial, the D-critical of degree NV doesn't contribute. Okay, they will contribute only in the part that is computed with the D-critical, but in the middle they do. Okay? Okay, then for example, in the example I gave, here you have a D-critical vertex of degree 2 attached to a vertex of multiplicity 2, then you can make it disappearing, and instead you have a D-critical of degree 1. Here we have 3 D-criticals of degree 9 attached to a vertex of multiplicity 9. You just can keep one. Okay? Then I will not explain this. It's a way to make reduction in series. And I go to the second part. And now I spoke about what happens around the vertex. I have a lot of numbers that divide the multiplicity of the vertex. Then now, using that, I will study paths in my tree. Then, if I have a pair VE, I define this number. This number is a rational number, and remember, D divides NV. C of VE divides NV. Then, this number, D over NV, is of the form 1 over an integer. This also. Then, now what I will do, if I have two pairs with this partial order, I said that VE is a comb over V dash E dash if and only if for all UF in between, I have epsilon of U equals 2 and my number R of UF strictly less than 1. And what does this mean that this number is strictly less than 1? It means that only one of the D's or C of VE is strictly less than NV. Okay? Then it is a very strong condition. And we come back to our tree. I put the vertices. I put in I put here the multiplicity, the DUs and the C's, and you see only one of those numbers is less than the multiplicity, which means that V4E4 is a comb over VE. Okay. Then this proposition explains exactly, we have a very precise description of the combs, which I show you on this drawing. Then you consider W0, W1, Wn, a pass with E1, En, and the C's are given by C of W1, E1 equals C1. Okay, we have that. And Wn is a comb over W1, E1 if and only if the W satisfies the following. If two characteristic numbers are equals, Cg equal Cg plus 1, then the multiplicity of omega g is a multiple of Cg, and it has attached a d-critical of degree exactly the same than the multiplicity. And now, if Cg is greater than Cg plus 1, then the multiplicity of omega g is Cg, and it has attached either a vertex of valency 1 with multiplicity Cg plus 1, or a d-critical with degree Cg plus 1. Then we have a complete description of the combs. Then, now, the third step, I want to study the whole tree. Then I consider a reduced tree. Then we can prove that the only possible vertex such that epsilon equals 1 and delta of V negative of 0 is the root. Then, if the tree satisfies this property, we said it satisfies property star. And we declare the attraction point of the tree to be V0. But if we do not have this property, we take any of the vertices with epsilon of z equals 1, and we declare it to be the attraction point of the tree. Then, now we have a tree, and we declare an attraction point. Okay? And what we will do, we will consider now the special pairs from any V. We consider the edge going to the attraction points. Then we have a special set of pairs VE. And on this set, we declare the equivalence relation VE is equivalent to U, E, EU, if and only if one is a comb on the other one. And then we have a set of equivalence classes, and one of our main results is the number of equivalence classes is less or equals to 1 plus 2 times the genus, and if n is not reduced to V0 and the number of equivalence classes is exactly 1 plus 2 times the genus, then condition star is satisfied. Then, first example, if the genus is equal to 0, condition star is satisfied, and we have only one comb. Okay? And we know for this twist that the monodromy is semi-simple. And why the monodromy is semi-simple? It's because the Alexander-Dymka polynomial is equal to 1. But actually, I wanted to understand from the combinatorics why we have this property, and using the computation of Heisenberg and Neumann to compute the Jordan block of the two of the monodromy. And actually what we can prove is that if a polynomial satisfies star and has only one comb, then the monodromy is semi-simple. Okay? Then here I have a description, then I have taken two examples, polynomial of genus 0 and polynomial of genus 1. Genus 0 is quite simple. Then the reduced tree of polynomial reduced polynomial of genus 0 are those two examples where V1 E1 is a comb of V1 E1, and we know how are the comb, and actually we can compute by induction on the numbers E1 and D. Then polynomials, reduced polynomial, reduced rational polynomial are known now. For the genus 1, it's more complicated, but we can describe everything. Then if the tree satisfied condition star and with one comb, V1 E1 is a comb of V1 Vn En is a comb of V1 E1, then the Vn have very precise description, and then we have all the possible Alexander-Dymka polynomial, and the other cases, this is the case where condition star is not verified. Then you have at the end two vertices with delta equals 1, and in the middle delta equals 0. You have here example with two combs, and you have here that the possibility with two combs is this one, and the possibilities with three combs is this one, and you can describe completely the vertices. Then in this I gave three examples for A, B, and C, And in these three examples, each time we find that the Jordan blocks, we have Jordan blocks of order 2 in the three examples. Okay, then stop here.
So if there is a question, I don't think we have microphone, but some questions, remarks? No? Sorry.
Thank you very much, Pierre. So there are several questions, but probably it will not be too long. So in that case, you could also find these Jordan blocks. So you make so you have the trees at infinity, but making something like the semi-stable normalization, you may have some graph over this, and if the cycles of this graph may also give these Jordan blocks.
What I use the computation in Eisenberg and Neumann book, Theorem 40. Then it's complete. I don't know much about it. I just make the computation. What is interesting with the cones is that in this computation of Eisenberg and Neumann, you have many edges that can contribute, but from the cones, you can see that blocks are equal to 1 in each cone, and you just have the connection of two cones to check actually.
Okay. Any other question or remark?
You can do this construction over one field of characteristics positive.
Actually, it's combinatorics possible. Then
you define some, as far as I understand, you consider graphs which just satisfy some combinatorial properties. And as far as I understand, trees at infinity satisfy these properties, but it is not equivalent. Is it, how to say, necessary and sufficient condition for a graph to satisfy, to be a tree at infinity? You at the beginning of your talk, you listed properties 1, 2, 3, 4, 5, 7, I don't remember how much.
Then I study these trees with all these properties, and I get, but what I don't know, if all the trees you get are trees coming from polynomials.
But the theorems you formulated, you prove it just for these combinatorial objects.
Yes.
Okay, so any other question? I don't see very well from here. Okay, so I have a remark for the audience, not for Pierrette, she knew very well. So the name of Newton trees come from the fact that they can be computed from the Newton polygon. And this is very interesting for the Jacobian conjecture because Jacobian pairs has proportional Newton polygons. That means in the successive steps. That means that for a Jacobian pair, they have the same Newton tree until the very end. And one way to tackle the Jacobian conjecture is to understand what happened at the end, including the critical that Pierrette taught. So this is really interesting for the Jacobian conjecture. So. So,
But it's not
well, the history is not finished, so we cannot we cannot tell how we will finish. Okay, so thank you very much again. This is explained, the talk I'd like to give is a little bit explained by the subtitle, A View of June Ha's Keller Package. I'm going to follow this from Prelude up to Outlook. The rest are notes and an appendix. And it will be some combinatorics, the Veil conjectures, we will remind of that, the Lorentzian polynomials, the Keller package, and Outlook. The prelude is just who is June Ha. Well, the nomination for his Fields Medal about 1 year ago, July 2022, it was for bringing the ideas of Hodge theory to combinatorics. The proof of the Dowling-Wilson conjecture for geometric lattices, the proof of the Heron-Rotta-Welch conjecture for metroids, the development of the theory of Lorentzian polynomials, and the proof of the Strong-Mason conjecture. Quite possibly, if I had read all of this, maybe I wouldn't have paid much attention, but when I saw Hodge theory, I think all my body was just a big antenna about what was going to happen. Well, the Fields Medal was awarded on 6 July 2002. The title of his lecture was Combinatorics and Hodge Theory. Is reference 1 in these slides. And the paper in the proceedings is number 2 in the references. And the laudatio is number 3. June Ha actually was born in Stanford in 1983. But he grew up in South Korea. Her parents were doing the PhD in Stanford, and once they finished, they moved back to South Korea. There, he followed a master's degree at the Seoul National University between 2002 and 2009, and this I should investigate a little bit more what it means. It was mentored both in Korea and also in Japan by Keisuke Hironaka. He did the PhD at the University of Michigan in 2014 under the advice of Mircea Mustacha, an algebraic geometer. And he has been at the Institute of Advanced Study at Stanford University and Princeton University. Now, let me see if I tell a few things about combinatorics. I feel good about the previous lectures because there was a lot of combinatorics, but here will be just combinatorics for its own sake. Here you have Hassler-Whitney. He wrote one of the first papers in graph theory, as you can read in the slide. He was one of the founders of singularity theory, as all of you know here, and he did foundational work in manifolds, embeddings, immersions, characteristic classes, and geometric integration theory. I think it is interesting that, in some sense, modern graph theory was started by this kind of works. And it was also published later on the Transactions of the American Mathematical Society, as explained in the slide. And then I think that I have to say a little bit on another work of Whitney, which is the introduction of the matroids. Basically, they are defined by the properties A and B in this slide. A matroid somehow axiomatizes the notion of a set of finitely many vectors. And Among these vectors, there are the independent sets, and they satisfy that a subset of an independent set is independent, and then that if you have sets NP and NP plus 1 of independent sets of P and P plus 1 columns of a matrix, you may imagine the vectors to be columns of a matrix, then NP together with some column of NP plus 1 forms an independent set. This is obvious because of linear algebra. But the main point is that what he says here at the beginning of this paragraph, that these theorems, he calls it A and B theorems, are not, there are other theorems, sorry, that are not deducible from this. And he discovered actually that because of the relation between metroids and graph theory of graphs. There is a book by Wells written in 1995 called Metroids Fundamental Concepts, in volume 1 of the Handbook of Combinatorics. The Handbook of Combinatorics is more than 2,000 pages, and the editors were Graham, Gretschel, and Lovash. As the word suggests, Whitney conceived the metroid as an abstract generalization of a matrix. And much of the language of the theory is based on that of linear algebra. However, Whitney's approach was also motivated by his work in graph theory, and as a result, some of the metroid terminology has a distinct graphical flavor. Apart from several isolated papers up to 1949, the subject of metroids lay virtually dormant until the late 50s, when William Thomas Tutt, two papers in 1958 and 1959, published his fundamental papers on metroids and graphs, and rather, 1957, studied the representability problem of metroids. A metroid is representable if it can be, if it's isomorphic to the metroid of the columns of a matrix. Since then, interest in metroids and their application in combinatorial theory has accelerated rapidly. Indeed, it was realized that metroids have important applications in the field of combinatorial optimization, and also that they unify and simplify apparently diverse areas of pure mathematics. About that, I want to read a sentence that is in his biography at the Wikipedia, because I think it's not very well known. During the Second World War, Tutt made a brilliant and fundamental advance in cryptanalysis of the Lorentz cipher, a major Nazi German cipher system which was used for top secret communications within the Wehrmacht High Command. And it is thought that this, of course, this is a parallel work to that of Turing deciphering the Enigma, but it is said that he also contributed a great deal to the end of the war. Okay, here are some selected references. Since the slides are available to you, I will give the link at the end. It's just because one has to be armed with several references on your desk if you want to understand a little bit all of these things. Among these, I think that number 5, Kuhn wrote a young combinatorics in a Rote way. It's a very nice book, and out of that and from many other sources, there is this identity, which I call it the exponential identity. Then, of course, this one I already mentioned. And as for metroids, I think the best one today is the Oxley book of 2011. But there are very nice summaries. One by Oxley of 13 pages is really remarkable. Another one from early this century, 45 pages. And there is one by the same Wells as before, 46 pages. And for people that are interested in the interplay between algebra, combinatorics, algebraic geometry, and so on, I think that these books are very interesting and necessary to do our work. The first volume is in the second edition and is of 2012. The second volume, there will not be a second edition, according to Stanley, and it's of 1999. Well, it will be explained when I go along. I have decided that a number with double square brackets, say this 36, refers to the reference item 36 in Haas paper in the Congress, which, if it's in my reference list at the end, I just quote it like this way. Such labels are linked to an outline to an online file whenever possible, and the correspondence with our reference list is indicated in red if it is included in that list. For example, number 13, Grothendieck 69, is the paper on the standard conjectures, which is somehow the kickoff of the kernel package. Well, let me do, in order to explain the contributions of Jun Ha and his colleagues, some background notions. Suppose you have a sequence of non-negative real numbers. This sequence is said to be unimodal if it is non-decreasing up to some point, and then non-decreasing from there to the end. I will call it a staircase if it's unimodal and symmetric. For example, the sequences of Betti numbers, even Betti numbers, V0, V2, V2n, or V1, V3, V2n minus 1 of a Keller manifold are staircases. I said that I have included an appendix. This appendix is, you go to the corresponding page to explain these things about Betti numbers in appendix 54, page 54. The sequence is said to be log concave if aj squared is bigger or equal than aj minus 1 times aj plus 1 for all j from 1 to n minus 1. A log concave sequence of positive terms is unimodal. This is very easy to prove. For example, the symmetric sequence of combinatorial numbers is log concave. Again, a simple exercise. And it's said to be ultra log concave if the quotient of aj by the combinatorial numbers is log concave. This can be rephrased in a way that I will look at it a little later. And a sequence is said to be top-heavy if aj is less than or equal to af minus j for all j up to the middle of the sequence. Now, for the ubiquity, because you say, why these sequences, why these definitions? Well, the ubiquity of these notions in algebra, combinatorics, and geometry, see the surveys 14 by Stanley and 15 by Brenty. Actually, Brenty explains the contributions of Stanley. For specific occurrences in the theory of projective hypersurface singularities, see the paper 16 by Hall. And a very recent one, I'm corresponding with our friend Paolo Lufi on part of these topics. And in this paper, which is from last month, there are a lot of examples and generalizations of the notions, as I said, coming from intersection theory. It's a person to follow if one has interest in these sort of things. Examples, there is a theorem of Newton that says that if you have a polynomial of degree n and you write it in this way, the coefficients you call Vj, or you redefine them as n over j times aj. It's a real polynomial with real roots. Suppose you get real roots. Then b0, b1, bn is ultra-log concave, or what is the same by the definition, a0, a1, and an is log concave. Moreover, and this is easy, this is not difficult to prove, but I think it's very interesting, a very nice exercise. If Vj is non-negative, then this sequence v0, v1, bn has no internal zeros. Well, this or the other one, of the a's. Internal zeros would be that there would be some zeros in between. Let me mention intersection cohomology staircases. If X is an irreducible complex projective variety of dimension n, not necessarily smooth, Goreski and McPherson, 19 and 20, the references, introduced the intersection cohomology of X, which is denoted with these funny symbols. It goes from degree 0 to degree twice n, twice a dimension, as it is as usual in complex manifolds. If you call beta j the dimension of this intersection cohomology, we may call them also Petty numbers, then the sequences of the even ones and the odd ones are staircases. For an overview of the development of intersection cohomology, see this very interesting paper by Kleiman of 2007. Well, now I can explain what, at least the contributions of Jun Ha and his collaborators. I start with a graph G with set of vertices V, set of edges E, and a positive integer Q. Then we say that a proper coloring of G with Q colors is a map that goes from the vertices to the set of integers from 1 to Q, such that C of A is different from C of B when AB is an edge. Well, you can do examples, simple examples, and then you could conjecture also this. The number of proper colorings of G with Q colors turns out to be a polynomial in Q. It's called the chromatic polynomial of G, of the form this one. Well, there is a symbol. Sorry that I keep confusing one thing with the other. Denote it this way, and I put the signs alternately. N is the cardinal of the number of vertices, and Aj is non-negative for all j. Now, the Ritz-Howard conjecture, 1968 and 1974, says that the sequence A1AN is log concave. It was proved by Ha in 2009 in his PhD research, doing the research for his PhD. And the sequence is also unimodal, just as a consequence, and this was the part of the Ritz in the conjecture. This turns out to be a special case of the conjecture that we consider next. It's the Heron-Rotter-Wells conjecture. Here, let me give one of the many definitions of a metroid. It just coincides with the initial one. A metroid is a pair of a set, finite set E, and a finite family of subsets of V, the subsets of I are called independent sets, and they satisfy what I said before. The empty subset is independent. This is why I call it I0. I1, any subset of an independent set is independent, and I2, if x and x prime are independent, and the cardinal of x is bigger, strictly bigger than the cardinal of x prime, then there exists an element in x minus x prime such that x prime joined with the element x is independent. Here there is no reference to the cardinal, not explicit reference to the cardinal of x prime, only that this is bigger than this one. Well, once more, a metroid is an abstraction of the notion of linearly independent sets or finite set of vectors in a k-vector space, and such metroids are said to be representable over the field K. It is also important to note that a graph, this is very important because it's the relation that Whitney discovered between metroids and graphs, that a graph gives rise to a metroid by declaring a subset of edges independent if it contains no cycles. Cycle is a list of edges that closes, that makes a loop, okay? For a metroid M, the rank of set X, any subset of vertices, is the maximum of the cardinals of independent subsets contained in X. It's a very natural definition. The characteristic polynomial of a metroid, which is also denoted, which is denoted in this way, is defined by, well, there is a sign corresponding to the cardinal of X, u sum over all subsets of V. You take -1 raised to the cardinal of X, and then the Q raised to the rank of V, so the whole set, minus the rank of X. And if you rearrange, you can write it in this way, where D is the rank of V. These, by the way, these numbers Wj, they are called Whitney numbers of the first kind. They were introduced in those papers I mentioned. The characteristic polynomial generalizes the notion of chromatic polynomial of a graph in the sense that the characteristic polynomial of the metroid associated to a graph is the chromatic polynomial of the graph. This, you can find this in Oxley, the book by Oxley, on page 588. Well, the Heron-Roto-Wells conjecture asserts that W0, W1, W sub rank of V, sub D, is log concave. And this was proved in the paper in one in the sense of Junha, and is the paper 22 in my list at the end. Then the Dowling-Wilson conjecture, we need another structure. Let L be a finite lattice, and let R from L to the natural numbers, its rank function. Finite lattices have rank functions. And let L upper K be the set of elements in L whose rank is K. And let D be the rank of the whole lattice. It's the rank of the maximal element. Well, L is said to be geometric if it is generated by L1, whose elements are usually called the atoms of the lattice. And if, furthermore, R satisfies the submodular property, namely this inequality here. This inequality will remind you of the Grassmann formula for the dimension of linear subvarieties of a projective space. There, if in that case, you would have the dimension would be equal. Well, the submodular is a weakening of that property. What does the Dowling-Wilson top-heavy conjecture of 1974 assert? it asserts that the cardinal of Lk is less than or equal the cardinal of Ld minus k for k up to the middle rank. It was proved in 41. I remind you that this link means that it links to the paper. Okay? In my list is 23, Ha and Wang, 2017. See also this paper, which is by Braden, Ha, Matherne, Bradfoot and Wang, 2020, for further enhancements. Well, the conjecture was praised for the lattice Lm of flats of a metroid M. Well, in a footnote, a flat is a subset of E that is maximum for its rank. It's a way of speaking, of course. Then was praised for the lattice of these flats. But this is not a more general statement than the equation star. There's one here for these lattices, as the class of geometric lattices agrees with the class of lattices of flats of metroids. This is in the book, for example, of Oxley. Mason's conjecture let Ik, is again about matrices, let Ik, depends on M, be the number of independent subsets of cardinal K in a finite metroid M. Mason's ultra-strong conjecture says that the Ik form an ultra-concave sequence which can be rephrased. I gave the definition before, but a little computation says that is equivalent to say that Ik squared is bigger or equal than, well, Ik minus 1 times Ik plus 1, but with these numbers that are bigger than 1. 1 plus 1 over k, and 1 plus 1 over n minus k, where n is the cardinal of the number of x's. This was proved in 17 in his paper, 25, which was Brendan and Ha, 2020. And as expected, this I think is important because Vinzan, I think, is doing very, very powerful work. In a footnote of this paper, says that it was independently proved in the series of papers 2, 3, and 4 by, they are in 26, Anari, Liu, Garan, and Vinzan. Of course, if you would click here, you would go to the references and find out. This is not, of course, to belittle Anari, Liu, Garan, but as far as I have been able to see, Vinzan is the leader of this group. Well, I think the subtitle also speaks for itself, when the discrete charm algebraic geometry. This is not actually correct, as we have seen in the previous lectures, and there will be many, many examples of discrete reasonings before the various conjectures, but I think this is one of the main ones by the time it was done and by the consequences it had, and sure enough for the killer package that we are going to talk about. Well, this concerns the Hasselbalch-Zeta function, which is defined, it's a variety defined over a field Fq, finite field Fq, of Q elements, and it is the dimension of X. NR is the cardinal. NR is the number of points in X that are rational over Fq to the R, an extension of Q, and Cx is defined like this. Well, this, to a beginner, it would seem very strange that you define that, but this, if you would read papers on the exponential generating functions, then it is very clear, and you can recover the numbers N-R. Is examples for the affine space. The zeta function is 1 divided by 1 minus qn to t, and is a dimension of the Weyl space. because the number nr, in this case, is obviously qrn, and therefore when you substitute by the exponential identity, you get this formula. It is also trivial that if you have y an open set of x, then the zeta function of x is the zeta function of y times the zeta function of the complement of y in x. Because clearly the nr are the sum of these two, and when you exponentiate it becomes a product. And for example, the zeta function of the projective space will be the zeta function of the affine space of dimension n times the zeta function of the complement, which is projective space of dimension n minus 1, and then by induction it will be this product. So the highest one is qn, and then it goes down, qn minus 1, all the way down to 1 minus t, which is q to the 0. Well, Weil, again, a very interesting paper, paper 27 in the reference list at the end, just studied this kind of manifolds, hypersurfaces of this form. By the way, Harson, in his appendices of the algebraic geometry, he takes all the exponents to be equal, and he calls them Fermat hypersurfaces. But I think that they work much more generally. Okay. At the end, I think that I should quote, Weil says, this will contain nothing new. He speaks about his paper on the projections, except perhaps in the mode of presentation of the final results, which will lead to the statement of some conjectures concerning the numbers of solutions of equations over finite fields, and their relation to the topological properties of the varieties defined by the corresponding equations over the field of complex numbers. So, he is just saying that you can take solutions over a finite field, or you could take solutions over the complex numbers. It will be a manifold, complex manifold. And he says that the relation to the topological properties of the varieties defined by the corresponding equations over the field of complex numbers. I think it's a very deep statement having related these two things. Anyhow, if you let g of x be, let me show it this way, be the zeta function of x for non-singular projective algebraic variety, in this case is non-singular, over fq, then first conjecture is called rationality. It says that it has this form, a quotient of a product of polynomials. Upstairs you have odd indices. Downstairs you have even integers, indices. And the Pj are polynomials with integer coefficients, with always p0 of t equals 1 minus t, and p2n of t equals 1 minus qn to the t. The example of projective space is immediate by the formula I told you, but we have to check a little bit, but it's fine. But it is numerator 1 and denominator a product. So the odd polynomials are 1, and the even polynomials are the ones I just quoted there, or written here. He also conjectured the W2, these functional equations, that the Zx of 1 divided by q to the n t will be the zeta of xt times a power of t and a power of q and maybe a sign. And here E is the Euler characteristic of x. Well, actually, I do not have time to say this, but the example I think is clear. If you take x equals to the projective space, this map replaces this factor, the denominator of the zeta function, by this function, and then if you multiply by the denominators, you get that this can be replaced by this, minus q to the n minus a times t times this, which is one of the factors of the zeta function of the projective space. Hence, at the end, it replaces z of t by z of t times t to the e times this and this, where e is n plus 1, which is the Euler characteristic of Pn in the sense of the Chow ring or cohomology ring, because they have the form polynomials with integer coefficients modulo the ideal h to the n plus 1. So there are n plus 1 components isomorphic to z, and this makes up, and they are even, and therefore the characteristic is n plus 1. The Riemann hypothesis, let us denote the roots of Pj of t by this form. This is Bayes' notation. And the Riemann hypothesis, W3, is that the modulus of these roots, if there are roots, if the constants do not have roots, then this modulus is q to the j divided over 2. And it's called the Riemann hypothesis because if you replace the t in the zeta function by q to the minus s, then it becomes the usual equality of the real part of the zeros. Not to 1/2, but to j over 2. Okay. Now again, for the projective space is very clear. And the Betti numbers is the part, the topological part. If x prime is not singular projective variety defined over, well, you could take the example of Weil, but it is something defined over a number field embedded in C, for example Q, and it has good reduction modulo subprime ideal to a variety over the finite field Fp. Then the degree of Pj is the Betti number of this complex variety. In here I have put two important references. Carlson, because he explains the Weil conjectures and the history and so on, up to 1977. And then there is this book, I think it's very interesting. This is Motivity Integration by Chamberlain, Nikas, and Zeva, 2018. It is a book that won the Ferran-Soler-Balaguer Prize in 2018. And I have not resisted to put here a paper over curves because we found an algorithm to compute the numbers for the case of curves very quick. We needed it for reasons of coding theory, in which you use points over a curve, defined over finite field, to produce codes, error-correcting codes. Well, I think I will be a little quick here. Serre produced this paper in 1960, a Kählerian analog of the Weil-Riemann hypothesis. You can find more on this on page 53. The standard conjectures of Grothendieck were produced in this paper. This is the famous Bombay conference. All the big guys were there at that time. And there are very good references, 32 by Kleiman in 68, and 33 again by Kleiman in 94. Weil's conjectures are formal consequences of Grothendieck's standard conjectures on algebraic cycles. So they are conjectures on algebraic cycles of varieties. They are phrased in terms of a Weil cohomology. I denote like this. For example, the Eladik et al. Cohomology. And they are inspired in Lefschetz theory, you can read here, and Hodge theory here. Actually, W1 and W2 could be proved using Grothendieck's formalism, but not W3, which was proved by Pierre Deligne in 1973, and it gave two proofs. Different, you can find their history here. standard conjectures, which remain conjectures in general, are the main inspiration of the Keller package. The first conjecture is analogous to Lifshitz structure theorem on the cohomology of a smooth projective variety over the complex field, and you can find the complex analysis of this here. And the second is a positivity statement generalizing Bell's positivity theorem for abelian varieties, and it is formally analogous to the famous Hodge inequalities, and is in fact a consequence of this characteristic zero. This is explained the classical part here. For a thorough discussion, can be found in Kleiman 1994. He says, we discuss the context in which the conjectures arose, the way they explain the Veil conjectures, and 8 important forms of the Lipschitz standard conjecture, and finally the Hodge standard conjecture and its implications. Well, I don't have time to explain the Lorentzian polynomials because I do not want to hold you hostages here before lunch. It's very interesting stuff. Well, this is, I took it from the lecture of Junha at the ICM. And the Keller package is just putting together in an abstract way what I have been saying about Lifshitz and Hodge. And it is explained here, the ingredients, the postulates for Poincare duality, Karl-Fletcher's property, Hodge-Riemann hypothesis, and so on. There are examples, for example, of course, for all of us, we have a cohomology of smooth projective varieties, for example, Eliadic. And in this case, the package is essentially graphic standard conjectures. It could be a polytope with some definition of AX, or it could be a metroid, and other things. Now, he has some strategy of how to go about proving conjectures using the Lorentzian polynomials. And here there are 2 slides, since it will be available to you. You can look at them, of how he proved, or they proved this conjecture. They conjecture the ring, the A would be this Möbius algebra, and so K of London, the Keller part, would be multiplications by positive linear combinations of the deltas, and P of L would be multiplication in HL composed with the isomorphism in here, Poincare duality. Unfortunately, this fails to satisfy Poincare duality because this is not true, and so they had to work a little harder, and here it is explained that with some nice diagram and using a variation of the intersection homology, they finally give the proof. There is an outlook which is basically for myself. I think that this is sort of putting together things that I'm interested in to work in the future if I have time and energy to do so. And in particular, I think there is always still the standard conjectures, and I'm sure that there are good connections with mirror symmetry and with the limited geometry, which are things that I've been working some time. And finally, thank you. Anna Demier helped me in the combinatorics part, and I'm very grateful to her. Thank you very much. So, is there any question or remark?
So for me, I don't know if it is necessary. So for big matroids, can see at least in the representable case are hyperplane arrangements. So this sometime, I don't know, time ago there were some works of Hilsenbrunn that he took combinatorial inequalities that they were unable to find without all these research. Callao finally would be. But now, in the case of non-representable macroids, I don't know if you can extend. For example, I think, like, so you take Pappus theorem, and you take a non-Pappus macroid. Yeah. So, can you find, did they use it also to find?
Not as far as I know, these kind of things, but I have not read all the papers. There are very many papers. Fortunately, they are very well written and very rigorous, and so I have to find out. But everything I have seen does not mention this word. But I take a note of this.
Only thing that in order to have a combinatoric unit, that the L characteristic has to have a compass support.
Nacho, I'm almost there. ¿Qué quieres? Oh yes, sorry. I put at the very beginning of the slides that all manifolds will be supposed to be compact, unless otherwise stated, okay? And in particular, when they are complex, they are compact. And the Keller manifolds are also compact. Is that what you asked?
The characteristic has to have with compass support in order to have a well conjectures.
Yes, yes. So is there any other question? If not, let's thank all the speakers. Now we can go for lunch.
Up to you guys. You are the. Oh. Alex is at the hotel, so if they are waiting for him, he's at the hotel. It's up to you. Let's see. I don't know. You have to. You have to turn it on. I can see somewhere from the butt.
Hello? Okay, welcome back. It's my pleasure to introduce the second mini course of the conference under the title of Fundamental Groups of Complex Projective Manifolds and their Alexander type invariants. And the mini course is by Laurentio Massin from the University of Wisconsin-Madison.
Thank you. I have to apologize for disturbing the siesta of some of you. To my defense, these chairs are so comfortable that you shouldn't be bothered by this talk, you know, just I noticed that earlier myself, so it's I remember from 14 years ago, I had very good memories from and very nice dreams from these chairs. All right, so we are here to celebrate two great mathematicians who influenced me a lot, both personally and mathematically. Also through some exchanges of students and postdocs. So Manuel, who just introduced me, was Alejandro's student, and he ended up being my postdoc. And two of our best students in Wisconsin are, don't remember if born, but at least raised in Zaragoza, Eva and Moises. So mathematically, of course, what I'm going to say here is the topic of choice, I guess, in Spain. Pretty much everyone I know in singularities has something to do with fundamental groups. This is always kind of puzzling for me, how well these people in Spain can calculate fundamental groups of complements of, I don't know, curves or things like this. I always say this is difficult and I wave my hands and they say, no, we can do it. So you still have to learn. And to my satisfaction, even my former student now calculates fundamental groups with ease. And maybe I can learn something in that direction. What I noticed also this morning was when I saw the nice picture that Patrick posted of himself and you guys drinking, is that I don't have such pictures of drinking. I have one with Nacho, but not with the two of you, so we should make up for it at some point this week. Okay, so let me start with the lecture today. I decided to give a broader picture at the beginning, stating some motivation and some general problems, and eventually specialize to fundamental groups of plane curves, for example, and Alexander type invariants and their various generalizations. So let me start. Feel free to raise your hand or just speak up if you want to ask any question. I'm not sure I see everybody, but if you just yell at me, I'll hear you. So the motivation here is comes from topology, namely every finitely presented group can be realized as the fundamental group of a manifold, of a real manifold of dimension at least 4. And as we all know, algebraic geometry brings some rigidity in, and then the natural question was posed by Serre, or at least it is attributed to him, is to try to answer a similar question in the complex algebraic setting. For example, which groups can be realized as, let's say, quasi-projective groups? So fundamental groups of complex quasi-projective or projective manifolds. As we'll see, maybe I should first say something here. By slicing with hyperplanes, or even planes in this case, and using a Zariski-Lefschetz type result, one can actually restrict to studying, for certain purposes, the class of fundamental groups of quasi-projective surfaces. Okay, so we'll see that if we actually, there are many obstructions to this realization, but if you are willing to give up the smoothness, for example, there are very important results by Kapovic, and we'll see next, Kapovic and Kolar, which say that every finitely presented group can be realized as the fundamental group of a complex irreducible projective surface with some mild singularities, which are simple normal crossing or Whitney umbrella type singularities. So here I emphasize the word irreducible because this is quite strong. If you want to drop this, you can actually do better in terms of groups. Every finitely presented group can be realized again as the fundamental group of something with just simple normal crossings, a surface with only simple normal crossings. But of course, in this case, their examples are non-irreducible. In any case, this is a bit more general than the question Serre asked, so I'm just gonna stick to fundamental groups of smooth varieties for the purpose of this talk. And again, I mean, you can do all sorts of things. You can think quasi-projective, projective, Keller, and so on. So I'll try to overview some things that are known, some obstructions, some counter examples to realizations, and work through some exercises a little bit. I was told some students are in the audience, so I will try to pose some questions for them, and then maybe the more senior ones can answer them. All right, so similar questions, as I said, apply to Keller groups. But in this case, one doesn't have this restriction, this reduction to the surface case, because there is no, at least to my knowledge, there is no Zariski-Lefschetz type theorems or fundamental groups in this case. But one can do a little bit in this direction, for example, using Kodaira's result, which says that in the compact complex surface case, with even Betti numbers, there is always, well, such a compact complex surface always deforms to a projective one. So at least fundamental groups are preserved in this situation for surfaces. And we'll see later, I'll mention this again, this is not true in higher dimensions, as Voisin showed. So this important fact, which I mentioned here, that follows from Kodaira's classification of surfaces, has some very important consequences when we couple them with Lefschetz type theorems in the algebraic setting. Namely, if pi is a finitely presented group, then we have the following equivalences. This pi can be realized as the fundamental group of a smooth complex projective variety, so this is what we call projective groups. Or by slicing by Lefschetz, this is the fundamental group of a smooth complex projective surface. Now, using Kodaira's, we can get to the setup of, well, here I'm saying a little bit more than it follows directly from what I said up there, but fundamental groups of complex projective surfaces are also fundamental groups of compact Keller surfaces. And then from Kodaira's result from above, these are also fundamental groups of compact complex surfaces with even first Betti number. So as long as surfaces are concerned, any positive answer for any of these 4 items would solve the problem that you're interested in of realizability. Okay? Now, some related open questions or some related questions. Of course, I said something here for surfaces. I said that if you... Yeah, here everything is compact, right? Projective, projective, compact, compact. For now, yeah. So this is the Keller group situation up there and relation to projective. So in this surface case, there is no distinction between Keller and projective groups. But of course, the natural question is, well, what can you say in general? Is any, of course, any projective group is Keller, but is any Keller group a projective group? And this is a very difficult problem, and there was some progress in this direction. Of course, in dimension 2, this is the previous result I mentioned. But more recently, this was proved, for example, for linear groups. So groups which admit, let's say, an embedding into some general linear group. This was Clodon not long ago. Then Clodon and some of his other collaborators, Höring and Lin, showed essentially what Kodaira did for surfaces in dimension 3. And this is much more involved. And then, not to put your hopes too high, but also perhaps this is not the right reason to say that one perhaps would be too optimistic to believe that any Keller group is a projective group. There is something that was unproved in 2004 which disproved this higher analog of Kodaira's theorem. Says that there is a compact Keller manifold which is not of the real homotopy type of any complex projective manifold. This, of course, this doesn't say much about fundamental groups, but at least the homotopy types are completely different matters. Okay. Yeah, go ahead. Sorry, I don't hear. What? Real homotopy types. Yes. All right. I want to mention this here as an open question, and I formulate it so that it has to do with fundamental groups. This is something that Hopf more or less left behind in some form, and then Zinger phrased or proposed something more general in the spirit of what I formulated here. So the fundamental group of what's called an aspherical Keller manifold. So this means that Keller manifold has the fundamental group pi, and it is also a k pi 1 space, has a well-defined Euler characteristic given by the dimension of the Keller manifold realizing the group. So the sign of the Euler characteristic is determined by the dimension of the Keller manifold realizing the fundamental group, realizing the group as the fundamental group. Not much is known about this, even in the Keller context. There was, of course, a big result of Gromov in this direction for negative curvature or things in that regard, and it was generalized later on by algebraic geometers. But in the aspherical situation, this is pretty much open. Okay. Now, another line of research in this direction is to find obstructions on the homotopy types of complex projective, quasi-projective or projective manifolds derived from the fundamental group or even farther. And for example, it is known that complex algebraic varieties have the homotopy type of finite CW complexes. And this is very specific to complex algebraic geometry. And if you actually work in the even more restrictive setup of affine varieties, so things which are subvarieties of some affine complex space, then the homotopy type has the dimension restricted to the complex, the real dimension of the homotopy CW complex is at most the complex dimension of the variety. So this is, for example, an instance of Morse theory, and it's a quite powerful result. But perhaps something even more interesting to this crowd, and something that I know the Spanish mathematicians work on a lot, especially in Zaragoza, are this cohomology jump loci, which I'm not going to talk much about, but these are, you're looking at, let's say, characters of the fundamental group whose associated rank 1 local systems have non-vanishing cohomology. And there are structure results. These are homotopy invariants of the variety you're looking at, and they have very nice structure results which impose strong homotopy restrictions on the variety you're looking at. So there are many structure results in this direction, starting with Beauville, Green, Lazarsfeld, Simpson, Arapura, Campana, and so on. I mean, Alex Suciu is here. He worked a lot on this also, and Budur Wang, and there are even, I guess, more recent results by Enrique Artal and Jose Ignacio and Dani Matei, right? So there is a lot of work in this direction, and I feel a bit bad because of lack of time for not going into it at all. But for example, this cohomology jump loci, they have essentially an algebraic structure, right? So they are unions of subtorics of the character torus, possibly translated by some torsion points. All right, so let me get back to our realization of quasi-projective or projective or Keller groups. So let me state a few facts, positive results, negative results, and whenever things are easy enough to be justified on the spot, I will state an exercise and then try to work it out together. And I hope this is useful for some of the more junior people here. So a very nice construction of Serre shows that every finite group is projective. So it can be realized as the fundamental group of a complex projective manifold. Since this was one of the reasons why I would have initially preferred to write things on the board, but maybe the argument is a bit long to be put on a slide, so I'll just say, if you haven't seen this, it's quite beautiful, and I would recommend the book of Shafarevich, where this is worked out. So it has to do with, first you reduce to the symmetric group case, and then you use this, symmetric product construction. And Lefschetz, of course. Okay, so this is a positive results. Finite groups are projective. However, on the negative side, as you'll see, many groups are not projective. And here I just give you the example in parentheses of a free abelian group of odd rank. And we already heard today an earlier talk about the Keller package and Hodge theory and so on. And of course, this is a very powerful thing to know about and to have about, and it is available in the projective or Keller context. And in fact, in this case, Hodge theory tells us that the abelianization of the fundamental group should have even rank. So if our group is of odd rank, then cannot be Keller nor projective. Okay, a few more results. Gromov, or at least I think Gromov, if I'm not wrong, maybe building on results of Kochik for surfaces, show that projective groups cannot split as non-trivial free products. So you cannot have two different free products, two different groups whose free product is projective. More negative results, since I heard this a lot these days already. A result of Carlson Toledo says that real hyperbolic groups are not projective. So fundamental groups of closed real hyperbolic manifolds of dimension at least 3. And let's not, I don't want to make you become too pessimistic, so on the positive side, though outside of the world we care about today, as long as you drop algebraicity, everything is realizable. So every finitely presented group can be realized as the fundamental group of some complex manifold, compact complex manifold, even in dimension 3. So the algebraic world is the one that's very restrictive. As long as you drop the algebraicity, everything is just like the real manifold situation, more or less. And this is a nice result of Taubes from 92. Yeah, I have to make the same disclaimer as Patrick. I did my best to put as many references out there as possible, but I'm sure I forgot some, and it's not by intention. It's simply either lack of space or I'm not aware of these results. All right, exercises. So now we start with homework. All cyclic groups are quasi-projective. So if I give you a cyclic group, there is always a complex quasi-projective manifold whose fundamental group is the group I give you. Shall we take a piece of paper and write down the result and vote? All right, so I will try to go slowly through this slide. I put a bunch of exercises here, and I'll try to give some hints, and hopefully the hints will give you enough information to answer this question. So I need to find some quasi-projective manifold whose fundamental group is the given cyclic group. I mean, cyclic group could be finite or integers, right? So a bunch of known results about curves. If I start with a smooth curve in the complex projective plane of, let's say, degree d, then the fundamental group is cyclic of order d. So this is something that, I mean, there are many ways of seeing this. And if you haven't seen it, this itself is a good exercise. The second hint I give here is that if I have two lines in the complex projective plane, then the fundamental group of their complement, well, first of all, the complement of two lines in CP2 has the homotopy type of what? What's the best student here? Alejandro. C star, okay. A circle, right. So the fundamental group is the integers. These two hints should give you the answer for all cyclic groups. So cyclic groups are quasi-projective. Next, all abelian groups are quasi-projective. Yeah, everything is finitely generated, I should say. I said from the beginning, finitely presented even. I mean, I started with finitely presented, right? But here I'm just saying everything has some sort of finite type. So I'm not allowing weird. Okay? So again, going to curves, I take R+1 curves in the complex projective plane. They are all smooth, and let's say di is the degree of each of them. And importantly, I'm assuming they intersect transversally, pairwise transversally. Then the fundamental group of the complement of this, what's called curve arrangement in CP2, has a free part given by the number of curves minus 1. And then there is a cyclic part, finite cyclic, Z mod D, D being the greatest common divisor of all these degrees of the components. Okay? I will say something about how to calculate, for example, fundamental groups later on, but these are the simple, so to speak, cases. All right, so this is yet another positive result. Again, all free groups, again, finite rank are quasi-projective. This is perhaps the easiest of all. Right, so why are free groups quasi-projective? They should, I don't know, bring to mind this wedge of circles or something like this, right? So just cook up a space, a quasi-projective manifold whose whose homotopy type is a wedge of circles. And here is the hint. Take CPU1 minus a bunch of points, and that will do the job. Okay. Let's see, more exercises. Finite index subgroups of quasi-projective groups are quasi-projective. Now, this is something you learn perhaps in algebraic geometry in some of the first lectures, that finite covers, let's say unbranched covers of quasi-projective varieties are quasi-projective. Okay? But these are important facts that we'll see later on, give us lots of kind of restrictions on what is or what, what cannot be. Better said, what cannot be fundamental group of this sort. All right, direct products of quasi-projective groups are quasi-projective. It should be easier, right? Products of such varieties are still of the same sort. And now I don't want to give you the impression again that everything is quasi-projective. So to put a cap to your enthusiasm, I'll just mention that there are examples, actually infinitely many non-isomorphic examples of non-quasi-projective groups discovered by Morgan and Kapovich Milson. And I'm sure there are other examples after that, but so if you think statistically, it seems that there are lots of things that are quasi-projective and also lots of them which are not. So this is quite a difficult problem to decide in general if any given group fits in one of these categories. All right, so this was the story about some exercises about quasi-projective groups. So now let me say something similar about the projective situation or Keller situation. Of course, these are more restrictive, right? I'm asking something stronger. I'm asking compactness now. Free abelian groups of even ranks are projective. So I told you earlier that free abelian groups of odd ranks cannot be projective nor Keller because they have the, the wrong parity by Hoche theory. But I didn't tell you that the ones of the right parity are actually Keller or projective. So why is that so? Well, these are abelian groups. They have something to do with abelian varieties or compact complex tori. So take the affine space and quotient it by one of these lattices of rank given by the real dimension of the space, and you get what's called the compact complex torus, and the fundamental group is exactly what they topologically these are just real tori of dimension 2n. Okay? And then I have the same game as in the quasi-projective case. So the Keller metrics behave well under unbranched covers and under products. So this will tell us that direct products of Keller groups are Keller, and also finite index subgroups of Keller groups are Keller. I am doing my best to pace myself, but I have the tendency of speeding up. So if you feel like I'm rushing through slides, please, slow me down. At least it should be possible to, I don't know, if you want to take notes, to write the statements down, it should be possible to do that. All right, so the story with finite index subgroup is again the story of Kähler matrix lifting to finite coverings. Okay. Now more interesting things. I mean, a little bit maybe not obvious things. Non-trivial free groups are not Kähler. So when I say they're not Kähler, they're not projective, right? Because projective implies Kähler, so I'm saying they're not Kähler, which also disqualifies the projective situation. So, so free groups are not Kähler, right? This is, remember free groups, or this kind of free groups earlier, they were quasi-projective, right? But sorry. As soon as I impose compactness, they get cut out from the list. And the story here is about finite index subgroups. So I told you earlier that finite index subgroups of Kähler groups were Kähler. But in general, such free groups, non-trivial free groups, have subgroups of finite index, but the wrong rank, the wrong parity rank. All right, more concrete examples. A free product of two Z-mod 2s is not Kähler. And the example is, the reason is exactly the same as before. There is a finite index subgroup of the wrong parity rank. So Z here is a subgroup of index 2. But of course Z, we said, cannot be projective. SL2Z, this is yet another interesting group. This one is not Kähler as well. And the same story has subgroups of finite index, in this case, which are free. So this kind of general statements that I list as exercises are good obstructions to realizing groups as Kähler groups. All right, it seems like these are all kind of, if you work a little bit, you get the answer. And then there is something more general. In fact, SLNZ for any n is not Kähler. But in dimensions higher than 2, you have to, I mean, at least the proof I know goes through non-abelian Hausch theory. So it's a little, it's more involved. Okay, so this slide contains both positives and negatives in relation to the question of being a projective or Kähler group. Any questions? Okay. Here is another remark. Yeah, go ahead. Yeah. Well, I think in algebraic geometry, if you fix the type of variety, like, I don't know. Let's see, Rodolfo works on that. Rodolfo should know the answer here. But what I'm aware of is that typically, this is very difficult to answer because the fundamental group is not strong enough to capture the algebraic structure. I mean, not always. I mean, if you have something like, I don't know, K-pi1 space, okay, then like an abelian variety or something like this, then I expect the structure is more on the, I mean, the structure is on the nose, right? The topology determines the algebraic structure. But otherwise, it's very difficult to. So these are very difficult, very important results, right? When you say, look, the fundamental group determines the whole algebraic structure. I mean, this is very strong, and I know of very few cases. Alex, you want to say something? Yeah. Well, I mean, I'm sure he means more than curves, right? But even for curves, I guess, yeah. So this is a difficult problem in general. Other questions? I mean, of course, you would like to have this Reidemeister moves and like you do with knots and things like this, but I'm not sure this is doable in the algebraic context. There are, as I remember, there are moves that people in, I guess, Mori, right, uses this. Yeah, maybe I shouldn't get into this. This is a completely different subject. I'm sure Rodolfo knows a lot about this. That's one of the reasons he's here, to answer the questions I cannot answer, right, about fundamental groups. All right, so here is yet another interesting example. So you may actually have a group that contains scalar or projective subgroups without themselves being scalar or projective. Right, and I give you here a very easy example. Take the fundamental group of the Klein bottle. This is not projective. And I put a y in parentheses, and by the time I end this sentence, we should perhaps have an answer why that's true. But it contains the Keller group, z squared, right? So why is the Klein bottle not projective? Let's see, a student can answer this. Sorry, why is the fundamental group of the Klein bottle not projective? Klein bottle is not projective, but the fundamental group. Yeah. So what's the fundamental group of the Klein bottle? What's the fundamental group of the Klein bottle? Or what's the abelianization, better said? Yeah, so B1 is odd, right? All right, so it is quasi-projective, right? But yeah, so it's not projective, but it is quasi-projective. Okay, oops. Let me also mention that it's also interesting to study various subclasses of these classes of projective, quasi-projective, or Keller groups. In other words, we have classes of groups which satisfy, let's say, they are fundamental groups of, I don't know, manifolds of dimension 5. And then I want those to be Keller groups or something like this. So subclasses obtained by intersecting various classes of groups. So, for example, Delzant showed in 2010 that if you consider a Keller group, which moreover is assumed to be solvable, then it is also nilpotent up to a finite index subgroup. So virtually nilpotent. Or there is a perhaps even more down-to-earth statement called Donaldson-Goldman conjecture. It was proved by Alex Dimka and Alex Suciu, and then Kochi gave another proof, which said that if you have a Keller group, which is also supposed to be the fundamental group of a closed tree manifold, then that group should be a finite group. Easy consequences, well, let's say the fundamental group of a closed orientable real surface times z, times the integers, is not Keller, because this is infinite, right? Okay, so what else? We have some local people here who studied, for example, quasi-projectivity of Artin groups. And again, there was some previous work by Dimka, Papadima, Suciu. So Blasco Garcia and Cogoludo wrote a very nice paper not long ago about these Artin groups. And I think I will stop with the general overview, and I'll move to the fundamental groups of actual hypersurfaces, hypersurface singularities. So everything I said so far was more or less an overview of what's desirable to know about realizability of groups in the Kähler or projective or quasi-projective complex. But now I'm going to specialize to some very special, I'm going to specialize to a very nice class of groups, which are fundamental groups of complements to hypersurfaces in the affine or complex projective space. In this case, we can use again this reduction to fundamental groups of plane curves in the affine space C2 or CP2 by slicing with a plane. And this class of groups was already considered by Zariski and Van Kampen in the 30s. And I think, of course, many problems that they left open back then or that became interesting from their work have been worked out by the group of people who are celebrating here today and their collaborators. And some of these problems are still open, and hopefully the students we see here are going to manage in 10 years from now to, well, for the next conference in 10 years from now. Have you started planning that one yet? We'll see some solutions to those problems. All right, so the question in this case that I'm going to restrict to is what groups can be fundamental groups of curves in C2 or CP2, what obstructions are there, and as we'll see, classical groups that people look at, let's say in low-dimensional topology like knot groups, many of them cannot be realized as fundamental groups of such curves, curve complements. I'll say more about this later, but typically, at least for me, this is kind of a very shallow ground. So when I talk about fundamental groups of plane curves, I usually have to move to the commutative world. Let's say move to homology or homology of coverings or things like this, or I can actually calculate something by hand. Of course, as I said, many people here can calculate fundamental groups by hand. And that's very good to know how to do. Another motivation for looking at fundamental groups of plane curve complements comes again, as I said, from Zariski. There is this Zariski problem about finding what's called Zariski pairs. So these are pairs of curves that have the same combinatorics. So if you look in the neighborhood of the curves, of the two curves, they look alike. But the way they sit in the ambient space makes them be different as curves. So the position of singularities, yes. Yeah. Zariski pairs, I believe so, yes. I was about to say that, right. Well, to my knowledge, is also one of, besides maybe Mutsuoka, is one of the ones who worked most on this problem of finding examples of Zariski pairs. And of course, Jose Ignacio also. So I'll actually state an example here, which I think is very important, and I'll come back to this later on. So Zariski already had this example of curves of degree 6, which have only 6 singular points, all of which are cusps. So cusps, we saw this earlier already in Patrick's talks. They are defined. These are defined by locally by x squared is y cubed. And Zariski showed that the way the 6 cusps sit in the ambient space, in this case on a conic or not on a conic, makes the fundamental groups of the two types of curves look different. So I guess in modern language you say the moduli space of such curves has 2 connected components. Yes, go ahead. At least 2. Sorry, my bad. I didn't mean to say Zariski showed. I meant to say there are two. Yes, okay. At least two, yes. And these examples were in different components. Right, thank you. It's always good to talk in front of the experts, because if you say stupid things, they correct you right away. Okay, this is actually already something that, and as we'll see, as I'll mention later on, this is something that has an impact on many things related to the topology of hypersurface singularities. The fact that, for example, we'll see later on, Betti numbers of projective hypersurfaces themselves depend on the position of singularities. There is a way to translate this problem about the complements to looking at Betti numbers of a projective surface. I'll mention that later on. And this Zariski example already translates into saying that, look, let's say the middle Betti number of a projective surface with isolated singularities even depends on the position of those isolated singularities. And this is something very difficult to handle in general. Okay, this is what I should say at the end of this slide. So, of course, there was a lot of work in this direction by people who are here today. Artar Bartolo, Tokunaga, Oka, Shimada, Iral, Kogoludo, and so on. I mean in the direction of Zariski pairs, detecting, finding Zariski pairs. I'm not sure I'm allowed to say this, but Eva told me they have a new example now, so Jose Ignacio and Eva maybe should talk about it. So, all right. Again, I bring up my incompetence when it comes to calculating fundamental groups. And at least maybe for convenience, let me say today that they are difficult to handle. And I want to support this claim by some results that were done over time. So, for example, there was a conjecture by Zariski, and again, I may be fuzzy here about who proved this. I'm not sure I'm right. Deline and Fulton, there are other proofs later on. If our projective curve has only nodal singularities, so only nodes locally defined by x squared equals y squared, then the fundamental group of the complement in CP2 is abelian. We'll see later on that nodal singularities can be ignored for many purposes. So if you have nodes as singular points, for the purpose of calculating Alexander type invariants, they are not there. But they are always useful for counting things. There is a result of Nori. Again, I put these names here again to my knowledge. These things may be known from other sources from before. If you have a curve in CP2 which has only nodes and cusps, let's say A nodes and B cusps, and I have this relation between the number of nodes and cusps and the degree of the curve, degree being D, so 2A plus 6B is less than D squared, then the fundamental group is abelian. So this says, okay, if I have only nodes, I know the fundamental group of the complement is abelian, but I can allow some cusps, but not too many, right? So I still want the number of nodes times 2 plus the number of cusps times 6 to be bounded by the degree squared. Then the fundamental group is still abelian. Again, from the purpose of Alexander type invariants, this is kind of like the trivial case. On the other hand, at the other extreme, there is a nice result of Tokunaga show that, again, having only nodes and cusps, but somehow swapping the inequality order. So now I want this 2a plus 6b to be greater than some expression in the degree of the curve. Then the fundamental group is not abelian. Okay, and now I give you this example about sextics with 6 cusps. And you may want to see where do those examples fit in, here or here. nowhere, right? So the Zariski pairs that, at least the ones I like to talk about, of degree 6, have A nodes, A between 0, 3, and 6 cusps, and they fail. I mean, this kind of numbers are chosen so that, so B is 6 here. They are chosen so that both of these inequalities fail. So then you can still be in both categories. So in fact, this will be the situation I'm going to describe when I talk about the example of Zariski, but at the level of fundamental groups. In one case, the fundamental group is abelian, in the other case, is not. And of course, for something like that to be possible, I'd better fail these tests, right? All right, I want to give you an example here that shows, later on I'll mention this as being one of the nice examples of knot groups that can be realized as fundamental groups, but I think this is an interesting example of a curve of Mutsuoka, and later on this was reworked by Andras Nemeti. So I have two integers, co-prime integers, and I consider the equation, well, x to the p plus y to the p raised to the power q plus something similar, but now with q and p reversed, and the variables y and z. Then the fundamental group of the complement is a free product of z mod p and z mod q. Let's see what we get if p is 2 and q is 3. Well, maybe I didn't mention what the fundamental group of the sextic with 6 cusps is, but in this case, let me just say that when p is 2 and q is 3, one recovers Zariski sextic with 6 cusps in the special situation when the 6 cusps sit in the ambient space in a very special position. They are on a conic. There are nice generalizations in a recent paper by Jose Ignacio and Eva, and I'm sure Eva will talk about it, so I'll not say anything here. And yeah, maybe before I say anything else, let me just say, so the problem here is the same, right? So I want to answer the question, or I better say I want to answer the question, what group is not or cannot be realized as the fundamental group of such and such? Because typically, unless you have a constructive, you come up with an equation and a constructive way of determining the fundamental group, you can't tell when something is the fundamental group. But it's somehow easier to say, look, I developed some algebraic invariants attached to the fundamental groups, and then by calculating those things which are supposed to be simpler than the fundamental group, I get enough obstructions that I can check on a given group algebraically. Okay, if those obstructions are all satisfied, I mean, if the tests are all passed, then you may try to sit down and try to calculate. If you have enough obstructions, you may try to calculate the well, it's a nice example which maybe has the right fundamental group. So this is one of these instances where, I mean, if I just told you in the beginning, well, give me a curve whose fundamental group is the free product of z mod p and z mod q, perhaps if you haven't seen this before, you'd have looked a bit puzzled. So this is one of those situations where you actually, I mean, you have to be lucky enough to sit down and get the right group. Okay, so when am I supposed to finish? Let me ask this. 5:15? Okay. So, since the fundamental group in general is harder to manage, I mean, again, I mean, you can calculate, you can find the presentation of the fundamental group, but you know the story, right? I give you two presentations and you don't know if it's the same group. One can still get a lot of information about the topology of a curve by looking at invariants associated to the fundamental group. So instead of calculating the fundamental group directly, maybe it's easier in many regards actually to understand maybe the abelianization of the group. Okay, that would be the easiest invariant to look at, but maybe other algebraic invariants. As I said, if I just give you two curves and I say, are these curves in any sort of by any sort of classification the same, you'd say, okay, let's calculate their fundamental groups. But these presentations may not be enough to tell you if these curves can be moved one to another by some projective transformation. So then, well, maybe it's easier to check, I don't know, do they have the same Alexander polynomials or things like this. So this is where I'm moving now. I'm moving towards trying to attach to a fundamental group Alexander type invariants. So for example, polynomials, Alexander polynomials or Alexander modules. We already saw these names coming up in Piret's talk earlier. But then there are other sorts of invariants which essentially say, well, besides looking at the fundamental group, you may look so looking at fundamental groups and subgroups is the same as looking at coverings of the complement of the curve. But you may say, okay, in addition, I may look, for example, at representations of the fundamental group. Or I can mix the two. I can look at coverings, but then representations induced on subgroups of the fundamental groups. And these kind of things generate various sorts of invariants, so Novikov type, Novikov-Betti type invariants, or L2 type invariants. And I actually plan to maybe go little by little, cover a little bit of each of these topics and deduce several restrictions on fundamental groups deduced from properties of this sort of invariants. And at the end, maybe I'll tell you, okay, this group cannot be the fundamental group of a curve complement, just because one of these obstructions is, is non-trivial. So I'm gonna, the goal is to derive rigidity properties for these invariants and later on to read off something about the group. Okay, maybe this is a good time to ask if there is a question. Good, so I'm gonna move to Alexander type invariants of plane curve complements. Let me set some notations. So I kept using earlier this C bar. So there is a reason why I do this, because I want also C and C bar. So C bar is meant to be like the projectivization of an affine curve. But I can of course just look at it as the zero locus of some homogeneous degree D. Oh, I didn't say there. Homogeneous degree D polynomial in 3 variable, which defines a curve in CP2, a reduced curve. For the things I want to say here, I will choose a generic line in CP2. Generic means, let's say it doesn't go through singular points, it's not tangential, so it's as transversal as it gets to the projective curve. And then I'm going to take the corresponding affine curve with respect to this generic line, which I'm going to call the line at infinity. So I dehomogenize. Let's say this L infinity is z is equal to 0. So I'm going to dehomogenize with respect to z, and I get a curve now in 2 variables, x and y. The equation will be little f. And this is really the complement of the projective curve of the intersection with the line at infinity. So these are, as we'll see, I prefer to look at the affine situation, but there is a lot of information that one draws directly from the projective situation as well. So from the point of view of fundamental groups, there is an extension of groups which relates the fundamental groups of the complement of the affine curve and the projective curve. and the kernel of the map induced by the inclusion is generated by this meridian that goes about the line at infinity. Here I'm kind of exaggerating a little bit, so I said that the fundamental groups carry essentially the same information. I put the same in quotations because, of course, they're quite different, right? But at least, for example, their commutators are the same, or, well, they share enough good properties. For what I care today is more important for me to work with the complement in the affine setting because the fundamental group is larger. So the complement, the affine complement, has more interesting coverings to look at. Okay? So I'm gonna call, this will be the name I'm gonna carry through till the end of the lectures. The affine complement I'm gonna denote by M, and the fundamental group of this affine plane complement I'm gonna denote by pi. Something I already mentioned, this M is an affine variety of complex dimension 2. So it has the homotopy type of a finite CW complex of real dimension 2. And the key player here will be, I mean, everything will be related to the first homology, which is the abelianization of the fundamental group. And in this case, the first homology has rank given by the number of irreducible components of the curve. This is easy to see with Alexander duality, for example. So the generator, geometrically, the generator of the homology are just these meridians about the curves, the irreducible components of the curve C. So each irreducible component, if I take a transversal disk to the smooth locus of that irreducible component, the boundary of that small transversal disk will be what we call a meridian. Those meridians generate the first homology of this complement. All right, so now maybe I'll start talking about classical Alexander polynomials. So there are there are several variations of Alexander polynomials, but this one, the classical picture, is inspired by knot and link theory, so it's the constructions are very similar. There is a way to associate to the complement. I mean, you can associate to the complement the covering for any epimorphism from the fundamental group of this complement M to the integers. But in this case, for example, I would like to work with a very specific one. You can work with any one you like, but I want to work with the one induced by the affine polynomial f, the polynomial f defining the affine curve C. So this f defines C, and if I restrict it to the complement of the curve C, it maps to C star. It induces a morphism, an epimorphism actually, on the fundamental groups. And I'm going to call this corresponding infinite cyclic cover, so Z-fold cover of M, I'm going to call it MC. It's called a total linking number infinite cyclic cover just by analogy with number theory or link theory, but, sorry, not number theory, sorry, knot or link theory. But as I said, I can associate, and we'll do later on that situation, I can associate such an infinite cyclic cover to any epimorphism from the fundamental group to the integers. It is called linking number because indeed it can be realized by linking this, if I give you an element in the fundamental group, there is a way to define a linking number just like you do in the compact case. Yes. Well, I guess that's what you do in the local picture, right? That's why Milnor fibers come in. In the global picture, of course, you can do it in the weighted homogeneous situation, I guess, or homogeneous. But I don't know. Whoever works with this is it's a very natural question, right? So can you replicate the Milnor fibration picture globally? Of course, there is no global Milnor fiber unless F is homogeneous, but yeah, that's more like a local construction. I'm not sure. Maybe can be done. This is a question I think I asked when I was starting to study this, because I also came from low-dimensional topology initially, but I'm not sure I convinced myself at any time since then until now that anything can be done in this direction. Do you have a Cypher surface in this situation? A global Cypher surface? Yeah, that's exactly the... In the projective case, yes. I mean, no. Yeah, but I can projectivize, right? I can work in the projective case and look at the closure of the curve union the line at infinity. So that's fine, we can do that. But I don't think that makes the problem simpler. Anyways, I mean, this is something that I guess it's a very natural question from coming from a low-dimensional topologist in general. Okay, so we have a z-fold cover. The deck group is the integers, and that acts on the homology of the infinite cyclic cover, besides on the infinite cyclic cover itself. So the homology of the infinite cyclic cover, let's say with with field coefficients, becomes a finely generated module over the group ring of the deck group. So this can be identified with Laurent polynomials in one variable. And this is what's called the Alexander module. Well, maybe I should say a nice result of Anatoly from the 80s, and it was reproved later on by others, Randell being one of them, showed that this homology group is in fact torsion over the Laurent polynomial module. So it's important here to work with the field coefficient because I want the PID. All right? So if you take the characteristic polynomial of the T action, so T is like the action of the deck group generator on this Alexander module, on this H1 of the infinite cyclic cover, you get what's called the Alexander polynomial of the curve, or of the fundamental group. So this is something you already saw in Piret's talk coming up, the notion. So now we have, for an affine curve in general position at infinity, how I like to call it, we have an Alexander module, which is torsion, and we have a corresponding order, how Milnor called it, namely the Alexander polynomial. So what do these invariants tell me about the curve itself? Well, maybe I should point this out, that also once you know a presentation of the fundamental group, which you can find, for example, using braid monodromy, Fock's calculus does the calculation of the Alexander polynomial just like in the case of knots. But again, I mean, this amounts to calculating the fundamental group first. So what I would like to do, or at least to say, I guess I'm done here, is to actually promote rigidity results about the Alexander polynomial and see how those reflect on the group itself. And later on, I will actually make use of this fact that the curve C is in general position at infinity. So in particular, there is a homogeneous polynomial defining the completion in CP2, and there are other nice invariants of singularities like the Milnor fiber that people are very interested in, and I would like to relate the Alexander polynomial to the say, Betti numbers of the Milnor fiber and see how one difficult problem translates into another difficult problem, which we cannot solve, but there is some progress in that direction in recent years. So I think I will stop here, and next time I will start with this slide, defining the Alexander polynomial, and then I'll start to this kind of divisibility results and this kind of rigidity for the Alexander polynomials, and we'll take it from there.
Are there any questions, comments?
Yes.
That you take this transversal line at infinity to become affine is probably more psychological. So in the sense that, like is written there, so if you do not do this, you would have the group algebra of the cyclic group, and basically the Alexander polynomial you are going to obtain is the same because, okay.
You are right.
But maybe for things that you are going to do later,
you see, I put Randall there also, right? So
yeah.
I wanted to fit both in. So Anatoly's result didn't assume transversality at infinity. You're right.
Yeah.
But later on, I want to relate to the Milnor fiber, and there it's. I want to relate to the characteristic polynomial of monodromy of the Milnor fiber.
Yeah, because I think in the case of Anatoly, because you also are interested in divisibility. But
I have to say, in my thesis, I also worked on Alexander polynomials for hypersurfaces with arbitrary singularities, and there somehow it was important to use transversality at infinity, because otherwise, it's one thing to say you have non-transversality at finitely many points, but when you have a big singular locus, then things get quite messy. So I put these things here because I want to also relate to what I did eventually, but you're right, you're perfectly right. This result holds no problem, and the construction itself doesn't require transversality.
Other questions? Okay, if not, let's thank you, Laurentio, again. We resume in 5 minutes. Second talk of the afternoon is by Patricio Almirón from the Mathematical Institute of the University of Granada. And his title is, according to page 1 out of infinity of his presentation, his topic is the intrinsic topological nature of the Poincare series of a plane curve singularity.
Okay, thank you. First, apologize about the title. I know it's not the same as exactly the same as in the web page. This is because of the National Agency of Accreditation and everything, because they like we to modify the title in the topic. So, okay. So this is a joint work with Julio José Moyano Fernández, and it is already available on the archive. And essentially, we went to study construction of the Poincare series of a plane curve singularity in some recursive way. But before to start, let me talk a little bit about the setting. So we are going to work with plane curve singularities with any number of branches. So we have associated a local ring. Then since we have a factorization of f, so we can define discrete valuation for each irreducible factor. And then we can define a value semigroup. I know that almost all of you know this thing, so I'm going to be a little bit fast in this part. So once the value semigroup is just the semigroup of intersection multiplicity with your curve, and each part is the intersection multiplicity with the corresponding irreducible component. Something important about this is that this is a combinatorial topological invariant. So we can define it from the algebraic point of view, but we have a topological meaning for this invariant. In the case of having just one branch, so an irreducible plane curve, observe that this is a semigroup over the natural numbers, which in fact have a finite complement. So since it has a finite complement, it is something called numerical semigroup. But when you have more than one branches, it's a good semigroup. We will see this later. So since we are in the commutative algebra setting, we have a invariant associated to this thing, which is a Poincare series. For the expert, please let me call it a Poincare polynomial, because I want this to be a polynomial. So essentially, you define the Poincare series as the generating series of the semigroup, kind of. But then you want to multiply it by some factor to make this a polynomial, and then you can divide it by this factor. We have a problem with this definition, that is the following. If you take just one branch, observe that if I multiply by this factor and I divide by this factor, I'm doing nothing. So I have a series. But I want to work with something that is a polynomial. So essentially for me, it's going to be this thing, but it doesn't matter. Okay. So we have this polynomial invariant associated to the semigroup. Let me focus on the irreducible case, because for us the main idea of the whole paper is we are going to try to understand what is happening in the irreducible case, which is easy, and then we are going to try to mimic this thing in the non-irreducible case. So in the irreducible case, as I told you, the semigroup of the branch is a numerical semigroup. This means that it has finite complement over the natural numbers, which directly implies that it is finitely generated. So this means that it has a finite number of generators, which at the end are coprime, because we need finite complement. But the main thing about this semigroup is that it can be constructed in a recursive way. Recursive way means the following. So you take the greatest common divisor of this of some generators and define this number. Is this quotient and this other quotient. So we start with the first two. This is a numerical semigroup again, because beta 0 bar and beta 1 bar can be non-coprime, but if I divide them by their greatest common divisor, now they are coprime, and it became again the semigroup of a plane branch. And we do this process again and again and again, and then we can reconstruct the whole semigroup by doing this kind of operation. This is a completely combinatorial operation if I define it like this. But observe that this is going to have an important algebraic counterpart, which is the following. You can define from the semigroup algebra associated to the semigroup. This is just an algebra. I know almost all of you know what is this semigroup algebra, but the main important fact is that this iterative process leads you to a decomposition of the semigroup algebra in the eth step in terms of the tensor product of the previous semigroup plus this other part we are going to add modulo 1 relation. So at the end, what we are going to obtain from this iterative construction is that the semigroup algebra of the irreducible plane curve associated to the numerical semigroup, this numerical semigroup, is a complete intersection algebra, which is very nice. And this is because of this decomposition. So we are going to have a tensor product decomposition all the time, modulo 1 relation. And as a corollary, since the Poincare series is related with the Hilbert series of the algebra, then the Poincare polynomial, or the Poincare series, here I am using the Poincare series, is has this decomposition, which is the Poincare series of in the eth step is the Poincare series of the previous step evaluated in t to the ni, which is going to be this part we are going to multiply here, times a factor coming from the new generator and the relation. So the new generator is going to be here, and the relation is going to give you this factor. So this iterative construction on the semigroup will allow you to compute the Poincare series in an iterative way. This is the commutative algebra setting and the combinatorial setting. But I told you that this is a topological invariance. So what we can do in the topological setting? In the topological setting, we have an irreducible plane curve, and associated to this curve, we have a knot. This knot is just the intersection with the 3 sphere, and we want to study the knot, so we are going to study the fundamental group of the complement of the knot, which is the usual way. So imagine that your semigroup has beta 0 to beta g generators. Then there is an old theorem of Zariski, observed the years, is almost 100 years ago. Zariski provides this nice description of the fundamental group of the complement of this knot, which is this presentation. So I give you this presentation together. You have this number of variables, you have these relations, and this is the fundamental group of the complement of the knot. In fact, this theorem of Zariski is a corollary of this theorem of Brauner. This is because when you do truncation of the knot, then what is known is that when you have an irreducible plane curve singularity, the corresponding knot is an iterated torus knot. So this means that it can be constructed by successive satellizations in the knot, and this satellization, when you apply Seyfertvan Kampen theorem, then you are going to obtain this presentation of the group. So essentially, this theorem of Zariski, which is very nice, is just a corollary of Brauner together with Seyfertvan Kampen. But this presentation is very nice. And now is the key idea of the whole talk is the following. Look at this presentation, and then we can see the following. So we can compute the monomial curve associated to the semigroup from the presentation of the fundamental group. How? And this is the key. So you are going to take the ring of polynomials, take the variables at the number of variables you are going to have in the presentation of the group. Then, usually you want to study the abelianization of the fundamental group. So you can look at the image of the variables here under the abelianization map. But when you look at the abelianization map, then this element that generates the group goes to an element which is of this form. And something which is nice enough is that also this relation becomes homogeneous relation in some important element. So the nice thing is that when you play this game, then you obtain a presentation of the semigroup algebra of the semigroup associated to the plane curve singularity. And from this point of view, it is natural to ask what is happening with the polynomial invariant associated to the semigroup algebra and the polynomial invariant associated to the fundamental group, which is, as Maxime has told you, the Alexander polynomial. So when you want to compute the Alexander polynomial, you need to go to homology, which is a visualization of the group. So the nice thing is that the process of iterated torus knot give you this satellization give you nice Mayer-Beatrice sequences. So it is kind of easy to compute the Alexander polynomial. So what you need to do is you take your knot, and your knot is coming from some satellization of something. So this is what I want to study, and then I take the previous knot, and I take the complement of the previous knot. I take a tubular neighborhood of the previous knot, and I keep the interior of this thing, and then I obtain the Mayer-Beatrice decomposition associated to the complement of the new knot, which depends on the previous knot. This Mayer-Beatrice is nice and leads to the universal abelian cover. This is important because since it is living in the universal abelian cover, now I am here, I can put the Mayer-Beatrice sequence and I obtain a decomposition of the module. So now when I look at this Alexander module, I have this theorem of Scheifer, which is coming from here, which tells you that the Alexander polynomial in this iteration is the previous Alexander polynomial evaluated in t to the ni times this new factor coming from this new part. But now, if you look at this expression, and then you look at the previous expression here, taking into account what is happening in the case when you have just two generators. In the case when you have just two generators, it is trivial to check that the Poincare series and the Alexander polynomial are exactly the same. So from this iterative process, it is just trivial to know that the Alexander polynomial and the Poincare series coincide in the irreducible case. So for us, this was the key idea, because we were thinking, okay, so we are doing this kind of satellization process, and from this satellization process, we are seeing that this iterative construction in the commutative algebra world is the same construction we are doing in the topological setting. And then our main goal was, can we compute the Poincare series in the non-irreducible case? This was much more complicated. And this question was, and this work was motivated by this fact, is that Campillo, Delgado, and Guseinzade proved that when you have a plane curve singularity with any number of branches, the Poincare series and the Alexander polynomial coincide. But the main fact was, can we provide a deeper understanding of this coincidence by making this recursive process? We think that this part that I'm going to tell you, we think that the answer to this question can be yes, but it's at the end, it's up to you to say if this is yes or not. So the main idea is going to be, as I told you, we are going to use that, we are going first to try to prove that we can compute the Poincare series in an iterative way, as in the irreducible case. And after that, to check that every operation we are doing from the commutative algebra world is coming from the topological setting. So let me tell you what are the main challenges of this fact. So in the irreducible case, everything is nice, everything is easy, because we have a finitely generated semigroup. Also, the generators are ordered in a very, very, very good way, which is this property. So we have these minimal generators, very good ordered, that we can read off in the dual graph in this way. So the dual graph has also just one geodesic from the origin to the unique arrow in the graph, and this geodesic also follows the order in the generators. So everything is easy. So when you want to compute something in a recursive way, you are doing everything in an easy way. However, what is happening in the non-irreducible case? In the non-irreducible case, we lost the finally generated thing, but still it is finally determined. what happened? We don't have this nice inequality. We cannot compare things. It is very easy because we are now not in the natural number, but natural number to the number of branches. So we are in a bigger space, and it is difficult to order the things. But still, this finally determined thing is due to something called principal values that is playing the role of the minimal generators. And here it comes the central role of the dual graph. Because in the dual graph, in both parts, we can read this, the principal values, the minimal generator. So now this dual graph is a tree. As Patrick told you, this dual graph is can be quite a mess, but you can find some order. But at the end, now we have a lot of arrows here. And the main thing is that essentially there is some distinguished point, which is going to be called start point, where we want to navigate. So at the end, this is very poetic, because at the end you need to learn how to navigate through the stars. But how to navigate through the star of the dual graph is always difficult, and we need to find how to navigate these star points. So let's present you the main ingredient of this thing, which is at the end you need, the dual graph can be very complicated, but at the end you only need to worry about the stars. So each time you have a star, which is a vertex of valency bigger or equal than 3, we may have in two different situations. Here you need to be careful, because observe that in the irreducible case, each time I have a star point, the star point has only valency 3. In an irreducible plane case, we have only star points of valency 3. When we have more branches, the valency can be bigger. Also, each time I have a star point, I have an end point. But in the non-irreducible case, I may have a star point, which is having a dead end associated, a valency of vertex, a vertex of valency 1, associated to that star point. So this is difficult. This is the main difficulty of this fact. But then, in this case, we only need to take care about a star point and its associated dead ends, which are vertex of valency 1, and some proper star point, that is this kind of point that I told you, that a special point that do not appear in the irreducible case. Okay? So, since we need to worry about this star points, and we want to compute this from the algebraic setting, we need to know what are the valuations at that point in the resolution. So this is a theorem of Félix Delgado, and he proved that the semigroup in the non-irreducible case can be determined just from the valuation in the star points. This is very important, because this is playing the role of the finite generators in the irreducible case. This is playing the role in the non-irreducible case. Observe that when you have something irreducible, then these are the minimal generators, so we are in the good generalization. But now we know what are the valuation in the star points associated to this branch, and then we have this. But how can we order this mess? Because at the end, we need to compute the Poincare series in a recursive way. To do recursion, we need some order. And the main problem here is to order this thing. So the step 1 of the proof is ordering the star points. To order the star point, we are going to use the Puiseux series. However, Puiseux series depends on the parametrization. So I need to give you something we call topological Puiseux series, but a canonical topological form of the Puiseux series. So every time you have a plane curve singularity, then you can construct from the branches Puiseux series, which depend only on the star points. This is easy to prove, but the main fact is that you are going to have Puiseux series for each branch, where the geodesic, you are going to have a geodesic for each branch in the dual graph. And then the idea is that you want a Puiseux series which reflect the geodesic in the equation. So now you are going to have a Puiseux series where each factor is associated to a star point in the geodesic to the branch. So the first lemma is that when you have this topological Puiseux series, then you can provide a good order in the set of branches. Moreover, this order is very nice because it will allow you to compute everything. Moreover, when you combine this order in the start points together with the geodesical order along the geodesic to the branch, then you can prove easily, well, not so easily. It's a bit difficult to prove because there is a step which is complicated. But you can prove that this induces a total order in the set of start points of the dual graph. So now we have a total order in this set of points, and the idea is to compute the Poincare series at each start point in a recursive way. So we are going to compute the Poincare series at the first start point, then the Poincare series at the second start point is going to be computed from the Poincare series at the previous one, evaluated in something, and some factor. This is what we need to check. Since I don't have time to explain this, I want to show you an example of how to order the branches. So the main problem here is that you can give me a Puiseux series, okay? You give me the Puiseux series, and I compute the topological Puiseux series, okay? But it depends on the data. So you give me this data and observe that the branches are 1, 4, 5, 3, 2. I want to navigate through the stars. So observe, if I go into this star, then this other star. But this is the first one. So if I want to go to the second one, I need to come back, go to the other star, and come in here. If I want, and now I come back and to the third one. This order is not good. So we need to prove that we can provide a reorder of the branches that induce this total order that we want to work with. So the idea is to work with truncations of the parametrization, which are not the usual truncation that you are accustomed. So you look at the geodesic to the first start point, and then you have a partition of the set of indices. And as I told you, the problem is that with this data, I have 1, 4, 2, 3, 5. If I want to do it smoothly, the nice way will be to have here 1, 2, 3, 4, 5, because I want to do it in some natural order. So the first lemma is that you can prove that each time you arrive to this start point, then you have an ordering that is natural, which means that you can always assume without loss of generality that you are going to have here something like this. Now you go to the first part, and then you have again two branches, and then the branches separate, and again you need to permute. So you need to perform this kind of operation. As you can, I mean, since I only have 45 minutes, I cannot explain in theory what is happening here. I need 3 hours to explain the whole things, but essentially you can check that at the end I give you the data, and I can assume without loss of generality that this is very well defined, okay? So now I have a good order for me. For me means the following. I arrive to one star, and this geodesic is maximal. So I'm going to here, and this is the first one. I arrive to here, and this is the second one. And then I come back here. And then again a maximal geodesic to the third one. 4, come back, 5, and I finish. Okay? So essentially what we are doing with the ordering is to take a maximal contact somehow. The maximal is going to be the first one. So if you have question. Probably yes, but as usual, we started, I mean, I always think about this using request, but at the end the main, it was working better using the dual graph because you have the geodesic in a good way. But the truncations you are using is in request. So essentially you are thinking in request and translate it to the dual graph. So probably in the Lotus will be read better, but as usual, At the end, you need to choose some way. Any more questions? Okay, so I continue. So you will be asking why this mess ordering the stars? Since I want to compute the Poincaré series, and imagine that I cannot compute the Poincaré series just looking to the star points. So we are lucky, and we have a theorem that is the main theorem of Campillo, Delgado, and Hussein-Zadeh, where they prove that the Poincaré series can be computed from the dual graph, but not only from the dual graph. The only relevant terms in the Poincaré series are terms associated to the star points. So this means that I can compute the Poincaré series just looking at the star points. This is important because now we are in the good setting. I have a total order in the star points, and I can compute my invariant from these star points. So now let's do the recursive computation. So if I am in the irreducible case, this is very easy, as I told you at the beginning of the talk. I have just star points. Each star point has an endpoint. These are minimal generators, and the recursion is trivial because the ordering in the graph is trivial. I just have one arrow, I have just one geodesic, and this is completely ordered. So everything works nice. But what happened in the non-irreducible case? In the non-irreducible case, I need to do induction on the star points, but I have several types of star points. First, I have star points before the first separation point. This is a part of the dual graph that is common to all the branches. Since it is common to all the branches, it behaves like an irreducible curve. So this is a part of the dual graph. Now I arrive to the first separation point where the geodesic start to work in a difficult way. To visualize this, you need to understand the following. Each time you arrive to this situation, somehow when you are in the irreducible case and then you are doing the blowing up of everything, kind of the centers of the blow up are canonically defined. If you are in the irreducible case, you have only one choice to do blow up. But when you have several branches, when the branches separate, then you have several options. Doing resolution of singularities doesn't matter which kind of center you choose. But in this case, what we are going to say is that, no, I have a distinguished center, which is first, then another center, which is second, and so on. This is what I'm going to do. And you are reading this in the dual graph. You arrive to the first separation point, and then you need to choose a direction. Since I have a total order in the star, I'm going first to the first direction. It is marking the first star point after the separation point. And now after the separation point, I have different types of star points. I have the star points, which are the usual ones. But I have these star points, special star points, that are called proper. And these points, the bad point, kind of, are points which are not corresponding to maximal contact values. Are points that have some contribution to the Poincaré series, but not coming from maximal contact. And these are difficult points. But from these three different types of points in the dual graph, we are going to give you three different types of splitting polynomials. Since I have three different types of points, I need to define three different types of polynomial. So the first one, imagine that I have a vertex of valency 1. If I have a vertex of valency 1, then I'm going to have an star point. And I need to check what kind of star point is this. So, first one, the star points before the first separation point. As I told you, this behaves as in the irreducible case. So, in the irreducible case, the easiest case is this one. I have just two generators. So, if I have just two generators, the dual graph has two vertex of valency 1, this one and this one. So I need two factors here, this factor and this other factor. And then you can compute, and then this is the Poincaré series. And again, imagine that I'm in this part, and I add just one new endpoint. Observe that now I don't have two. I am adding just one vertex of valency 1. And then this gives you this new polynomial, which can be encoded in this unique polynomial. Why it can be encoded like this? Because when you do the recursive computation, this factor is going to cancel out every time you do the computation. And when you arrive to the end, then you have this x minus 1, because you have the polynomial invariant and not the Poincare series. Now, you have the problem that what is happening with the non-common endpoints. In the non-common endpoints, you are going to add, again, a new block here. And this new block is going to give you, again, a new factor of this type. Okay, and now the difficult one that does the proper, these are vertex of valency bigger than 4, but also proper start point that I forget to put here. So essentially for each proper start point, this is the most difficult factor you need to control. Because when you have a proper start point, you have some situation like this. You are going to have here some other arrows here. Imagine that you have several arrows coming from this point. And then since I have here several arrows, the evaluation is a bit weird. I mean, I'm going to have this contact and this other contact with some packages. So you need to distribute, since you are going to have a value that is not a principal value of the semigroup, you are going to have a value that you need to distribute evaluations. And since everything is contact, so essentially you need to look multiplicities in this direction and multiplicities in this other direction, and then mix everything. So this factor is very difficult to manage, but you can play with it. Summing up, I know I'm going too fast, but I don't have much time. But summing up, I have 3 different types of polynomials. The polynomial P, which is this one, which correspond to common start point. The polynomial Q, that is corresponding to non-common start points. And the polynomial B, that correspond to proper start points. And with these 3 polynomials, evaluated in the branches now, I need to evaluate the polynomials in the corresponding branches with their corresponding multiplicities. I'm going to prove the splitting theorem. And also this is the main reason to do the talk in slides, okay? And I want to show you that this is highly non-trivial to prove that just with these 3 polynomials you can prove algebraically that this is going to be the way to compute the Poincare series. So we start. Base case, irreducible case. This is the easiest one. Again, we are working with the irreducible case. We play with the P polynomial. You evaluate it. Then you obtain this product. You divide by t minus 1 if you want the Poincare polynomial or the Poincare series. Every time we are working with it t minus 1. Now, the second case, which is now non-trivial, non-irreducible plane curve, is the case where all the branches are smooth and they separate at the same time. In this case, observe what is happening with the dual graph. The dual graph, formally you can think, the worst situation is that I'm going to have 2 vertex of valency 1. Okay, so this is this 2 Q factor, this one and this one. And then all the branches are in the same point. So, as you can imagine, this dual graph has no 2 vertices of valency 1. But what is happening when you put here a 1? If you put here a 1, look at this. If you put here a 1, then this cancel out and it became a 1. So, yes, here you have 1 vertex of valency 1, and then you have this proper start point. And imagine that you have all the branches separate at the origin, then this is not going to appear, the denominator is not going to appear. So you can check this. And now the second case is, imagine that not all the branches are smooth and they separate at the same point. We have this dual graph. Again, from the formal point of view, the best situation is to have 2 vertex of valency 1. Then I need 2 Qs, this one and this one. And here is where the ordering is key. The ordering is the following. The first branch is going to be here, and the last one is going to be here. So if the first one is going through here, I mean, if I don't have here a vertex of valency 1, this means that the curve is smooth because of the condition. And if the curve is smooth passing through this point, then this factor in the Puiseux series is going to have a P11 equal to 1. And the factor cancel out. It's a 1. And this is very important because it is really a switch on, switch off if you have an arrow here or not. This is very important. And then you can find this kind of decomposition. You are going to have these two factors here together with all the proper start point you may have here. So it's very technical to prove that. Now you need to check that the Poincaré series is this one. And now we start with the inductive steps. Here I'm going to pass the inductive step because this is going to be nice to see. This is the easiest one. I'm adding just one generator. This is one a bit more difficult. You add something that separate here. And the most difficult case is this expression, okay? So, as you can see, this is highly non-trivial because this expression, to work with this expression is not easy. But summing up, the general idea is the following. I order the... So, the general idea is the following. I order the start point. I prove splitting theorems, which means at each start point, I compute the Poincaré series as follows. The Poincaré series at the previous start point, evaluated some way, Q, B, Q. Always, it depends on the situation, I'm going to have this kind of decomposition. And now, I use the order together with the splitting to recover the whole dual graph together with the Poincaré series. So, theorem. We can, given a plane curve singularity, and you consider the set of start point, then you can assume, because you can check that there exists a total order in the start point induced by this topological Puiseux series. Then the Poincaré series can be computed recursively via truncation in this way. Okay, so I can finish the talk here because all my results are algebraic results. I mean, I have not used topology. We are working with Campillo Delgado Gussein-Zade theorem. We have provided some decomposition, and then we work to provide the recursion. And I'm not talking about topology. But now I would like to reinterpret everything in the topological setting. So the general idea was this one. So what happened here? So we have the Poincaré series, and then Campillo Delgado and Gussein-Zade provided this Acampo type formula for the Poincaré series. This Acampo type formula encodes both information, topological information and algebraic information coming from the evaluation of the dual graph. And now you have two options. Now you can go Eisenburg-Neumann. Eisenburg-Neumann proof this Acampo type formula for the Alexander polynomial. And then if you use Eisenburg-Neumann, then you have directly this equality. But observe that here, when you look at this line, you are looking at the final picture of everything. Then you have the dual graph. You have an expression, an Acampo type formula, and then you use this formula together with Eisenburg-Neumann to provide this equality. So our idea is, okay, I would like to know better what is happening. So I need to go to this recursive decomposition. So I go here, purely algebraic setting, and then I give this recursive decomposition. Can I go in this direction without using Eisenburg and Neumann result? And the answer is yes. Again, Brauner's theorem. The link is an iterated torus link. And then I can construct the link by successive satellizations. This satellization gives you a Mayer-Vietorist decomposition that allows you to compute recursively the Alexander polynomial. These are the theorems of Sumner and Wood. that you have a good decomposition of a good computation iteratively of the Alexander polynomial. It is very nice because the paper of Sumner are good. It's almost at the same time as Eisenhut and Neumann book. So it's nice because this paper has almost no citation, just 5 or 6 citation. But the Eisenhut-Neumann book is the most common book in this setting. But the nice thing is that here, when you look at this operation, then each step we have done algebraically can be translated topologically, because at each step the algebraic operation is exactly the topological operation. So then you can put this equality here. How? At each step you use Sumner's good together with the recursion we are computing. So each time we have a start point, we have a decomposition of the Poincaré series. This decomposition of the Poincaré series is the algebraic counterpart of the decomposition in the topological side from the Alexander polynomial. So as a corollary, you can recover this equality because with the Poincaré series and the Alexander polynomial without using Eisenhut and Neumann result. Some conclusion of this is that essentially we have provided a recursive procedure to compute the Poincaré series, and naturally this kind of technique can be go to the more general setting of valuations, divisorial valuation. I mean, at the end we are ordering something in the dual graph, and then you can compute everything. Essentially, is to give you an order and then to compute recursively the series. Also, this is for me the most beautiful thing is that Eisenhut and Neumann splice diagrams are things that are coming from the topological nature of the link, and the proof are purely, for me, are purely topological. But now what you are doing in the Poincaré series setting is that you are giving same result, but from the algebraic setting. And from the algebraic setting, then you can play the same game when you don't have a topological structure behind you. And I think this is the most important fact about this. And then, as I told you, this gives you a new proof of the coincidence between this. And it's up to you to decide if this provide a deeper understanding of the coincidence or not. And just to finish, since we are in a conference for some reason, for me it's an honor to speak here in the conference of these two greatest mathematicians. And also my apologies to Enrique, since I'm the only student of Alejandro that I'm going to talk. I'm going to say a few words to Alejandro. This is me and Alejandro eating in Bratislava in Andras Nemeti birthday. This was before the accident with the rent car, which we were in a trip, and then Alejandro put the ground fuel to the rent car. This was very nice because we get stuck in Bratislava the day before the conference. But Alejandro is always have a very good sense of humor, and also I'm very happy to be his student. I think Manuel will agree with me that Alejandro is a role model for us and has taught us a lot. And so congratulations, and see you in a few years. So thank you very much.
Thank you, Patricio. Yes, I agree. So, are there any questions or comments for Patricio? Enrique.
So it's so I find a very nice construction, and I wonder if so basically you are working with somewhat abelian invariants in some sense, because, and I wonder if, for example, something like the cipher form could be more or less achieved also in this inductive process, or maybe the intersection form is some basis of vanishing cycles. Because this could be nice probably there were very nice examples of Dubois and Michel where they had singularities with different topology but the same Seyfert form. And basically this was because there are some inductive processes which are exchanged in some sense, but maybe the family of more examples, even all examples could be obtained if one is able, as you do, in that way, but for a less abelian setting.
Yes, I mean, I think that everything can be generalized to a lot of settings, because at the end, one problem with, at least for me, I had with the Eisenbuch-Neumann splice operation and everything, is that at the end, somehow it doesn't matter the order that you do the things, kind of. Patrick knows this better than me, but kind of, again, you are gluing everything. It doesn't matter a lot in which way you glue. You only need to be careful about if they glue or not. The most nice thing from the evaluative point of view is that it matters. In the evaluative point, it's more sensitive, and then you need to be very careful how are you gluing, because it's careful. And we think that it can be generalized to a lot of settings, for example. And I would like to see some algebraic properties of this, of other topological or even analytical invariants coming from this setting, because it would be nice. I mean, working on that.
Very interesting talk. Could you give any other type of result relating the work done by Andras Nemeti with Haus?
Yes, I think you're referring the Andras and Beam results about the point. Yes, I mean at the end we are doing similar things. At the end, what you are doing is they are using splice decomposition, I think, and then you have motivic Poincaré series and everything, and then you have some splitting theorems. But in this case, what we have done is try to avoid the splice operations and try to prove everything in more classical way. And we were surprised to be able to do it without this splice machinery. We think this is good because at the end it could be helpful to generalize things, because when you don't have a topological, the problem with all the splitting theorems is that when you don't have a topological structure behind you, then you cannot play this game a priori. And then if you forget about that and then you understand how to play with these kind of things, then you can compute this type of recursive formulas.
Are there other questions? Okay, so if not, let's thank you, Patricio, again. And now there's going to be a poster session downstairs. We will show the posters by Ignacio Breva and Alberto Fernández from the University of Valencia. There will be a short presentation.